Now we've seen cross-validation in action, let's see some other important classification model evaluation metrics. And to do so, we're going to start a new heading here. It's so important to evaluate our models. Evaluation metrics. And the four main ones we're going to cover for classification models: accuracy. The next one is area under ROC curve. And don't worry if you're not sure what these are, we're going to go through them. The third one is a confusion matrix. Sounds fancy, right? And the final one is a classification report. So to start off, we'll keep it nice and simple. We'll do accuracy. So we'll remind ourselves of how we can train a machine learning model and evaluate it by importing cross-val score from Scikit-learn's model selection. And then we'll import our random forest classifier. Wonder if we can press tab. Yeah, there we go. Beautiful. We'll set up a random seed. And then we'll create our X data. And we'll create our Y data. Beautiful. Now we'll set up a test and train split. So we'll go here, X train, X test, Y train, Y test. Oh, actually, we don't need to because we can just use the cross-val score. So let's do that. We might put a little heading up here to make sure we know that in this case we're doing accuracy. CLF equals random forest classifier. And then we'll print out the cross-val score by passing it our classifier, our X data, and we'll do 5-fold cross-validation. Wonderful. So here we go. We got number of estimators will change. Getting this classic warning. So this is just a reminder. We can set number estimators to 100 and that'll get rid of that. Beautiful. So what this is going to give back is because the default score parameter of our classifier is the mean accuracy, this is what the cross-val score is measuring here. Actually, we might save this to a variable, cross-val score equals that, run it again. And then if we take the NP mean of cross-val score, we've seen this one in the cross-validation video, this is going to give us the mean accuracy of our model. And basically, this comes out as a decimal, but we can easily type this out to be print, actually F, heart disease, classifier, accuracy. So whether or not our model can classify whether someone has heart disease or not, given their parameters, we want to put in here np.mean cross-val score. We're going to times this by 100. And we want 2 decimal places. We maybe need a percentage sign on the end here. Beautiful. This is going to be cross-validated accuracy, actually. So that's important to note. Cross-validated accuracy. So that's not too bad, right? And what accuracy is actually saying is, given a random sample, given a sample that our model hasn't seen before, how likely is it to predict the right label? So if we have a look at our heart disease data, we might do it under this cell so it doesn't interfere with our Scikit-learn code. Heart disease, .head. So given a sample that looks like this, has age, sex, CP, TREST, TB, PS, COL, FBS, all these features, given a sample like that to our trained model, how likely is it to predict the right target? And in our case, our model's cross-validated accuracy is 82.48%, so around about 82.5. So that means 82, or about just over 8 times out of 10, our model will predict the right label given a sample, something like this, based on the original training data. So that's accuracy in a nutshell. What we're going to dive into next is area under the ROC curve. And if that sounds confusing, it's a bit of a mouthful, but we'll go through it. So that's kind of how you would present your model's accuracy. You'd print out something like this. Again, it returns by default a decimal. In communication style, it's easier if you represent it as a percentage. Now, we've just covered accuracy as a method of evaluating our classification models. And you might be thinking, why can't we just leave it at that? Well, as we start to go through these other metrics here, you'll start to understand why it might be important to get a few more different evaluation metrics on the board rather than just accuracy. In my case, when I was first learning how to build classification models, I would always think, yeah, just higher accuracy is better, right? And then slowly after looking at different examples, I started to realize, okay, now I see the value of using other metrics like these. But let's not talk about it. Let's see it in action. The next one we're going to cover is the area under the receiver operating. So area under the receiver operating characteristic curve. The beautiful thing is it's also known as AUC, so area under curve, or ROC, so receiver operating characteristic. So let's do this. ROC curve. So these are the two things you'll look out for. Area under curve or ROC curve. Maybe we'll put it here. AUC or ROC curve. Beautiful. So if you hear someone talking about AUC or ROC or ROC or something like that, they're probably talking about this metric here. Now, what does a ROC curve measure? Well, by formal definition, a ROC curve is a comparison of a model's true positive rate, aka TPR, versus a model's false positive rate. Let's write that down here. Are a comparison of a model's true positive rate, which is also known as TPR, versus a model's false positive rate, which is also known as FPR. Now you might be wondering, okay, what is a true positive and what is a false positive? Well, let's have a look here. A true positive equals model predicts 1 when truth is 1. Does that make sense? So in our case, if we have a look up here, if our targets are 1 or 0, a true positive is when our model predicts a 1, the real label is a 1. Okay, yeah, that makes sense. So if we go here, a false positive is model predicts 1 when truth is 0. So why is it called false positive? Well, it's because it's predicting 1, so aka the positive class has heart disease, when the truth is actually 0. So it's giving us a false positive sense that a person may have heart disease in our particular case for our heart disease classification problem. And then if we go here, a true negative equals model predicts 0 when truth is 0. So that makes sense. So that's predicting the model is getting the right prediction there. It's predicting someone doesn't have heart disease when they actually don't. That's great. And then a false negative equals model predicts, what do you think this one will be? False negative. If we look at false positive, a false negative is when model predicts 0 when truth is 1. So that's because it's predicting not heart disease when it actually is heart disease. Right, so now we know these, we can see that a ROC curve is a comparison of a model's true positive rate, TPR, versus, typos everywhere here, Daniel, come on, versus a model's false positive rate, or FPR. So now we know this, let's see it in action. So we can do this using Scikit-learn's metrics library. We're going to import ROC curve. So see how I was saying, ROC curve, ROC curve, and then we're going to make predictions with probabilities. And how can we make predictions with probabilities? We saw this in making predictions. We can do that with yprobs equals clf.predictproba for probability. We're going to make some predictions on the X test data. Now, I just want to make sure, maybe we do that, we create X test, just to make sure it's the right X test data, X test, etc. So we want to go here, X train, X test, Y train, Y test equals train test split, X, Y. Test size equals 0.2. Wonderful. And so now we can do that there. Because a ROC curve is a comparison of a model's true positive rate versus a model's false positive rate, we want to only keep the positive classes. So actually, let's see what yprobs looks like. Yprobs, why hasn't this worked? What do we got here? This random forest classified is not fitted yet. Call fit. Ah, that would make sense. So we want fit the classifier. Of course, you can't make predictions without fitting them, without the model learning any patterns. So we're going to fit it here, then we'll make some predictions, and we'll have a look at this. Maybe only the first 10, so we're not taking up heaps of space. Okay, beautiful. And so because ROC curve only is a comparison of a model's true positive rate versus a false positive rate, we only want probabilities that the model has predicted for the positive class. So if you imagine here, our model's trying to predict 0 or 1. This is the probability that the label is 0. And this is the probability that the label is 1. And so on for all of these samples until it finishes up. So there's going to be, however many are in the test set here, 61. So there's going to be 61 of these. So essentially what we want is y probs positive. So this is the probabilities that it's the positive class, aka 0 is the negative class, and 1 is the positive class. Y probs, we're going to use some slicing here, but only column 1 of every row. So we can do that, just so you know what's going on. Positive. And we'll only look at the first 10 again. So does this make sense? We're getting 0.43, yep, 0.77, yep, 0.48, so on, so on, so on for the entire list of Y probs. And now we can calculate FPR, TPR, and thresholds. So we'll go FPR equals TPR, thresholds. Why do I know this? We'll see this in a second. Why do I know that this is going to be FPR, TPR, thresholds? We got ROC curve. We're going to pass it Y test and Y probs positive. Now, how would you figure out what ROC curve returns in this case? Well, what I would do is I'd press Shift Tab, and this is how I know. So we got ROC curve, it takes Y true, so that's our test labels. It takes Y score, so that's our Y probs positive. And if we come down here, compute the receiver operating characteristic, ROC, yep, beautiful. Now parameters, Y true, Y score, target scores can be either probability estimates of the positive class, confidence values, or non-threshold measures of the decision. So that's the probability estimates of the positive class. That's where we got this slice from, right? And then if we come down here, it's going to tell us what it returns. FPR, increasing false positive rates such that element I is the false positive rate of predictions with score above thresholds. TPR, so that's a true positive rate, and thresholds. So that's how we can figure out what a function returns. And again, that's just viewing the doc string in a Jupyter notebook. You can always look at the documentation for this. If you wanted to do so, you might look up something like how to calculate ROC curve for Scikit-learn. So then we're going to check the false positive rates. FPR, beautiful. So that's giving us a big array. But looking at these on its own doesn't really make much sense. It's much easier to see it visually. And since Scikit-learn doesn't really have a built-in function to plot a ROC curve, what we might have to do is, and quite often you'll come across this, right, is you'll have to find a function or write your own that'll do it for you. So that's what we're going to have a look at in the next video. We'll plot a ROC curve, and this function here, ROC curve, will start to make a bit more sense rather than just be an array of numbers. So we left off in the last video calculating our model's false positive rate, true positive rate, and at what thresholds using the ROC curve function. Now, we kind of got back the false positive rate, but it's in an array of numbers. So looking at this, again, doesn't really make much sense, but plotting it and seeing the ROC curve, the actual ROC curve, will make a bit more sense. What we're going to do is we're going to create a function for plotting ROC curves. Now, in your practice, when you need to make multiple plots, as we saw in the matplotlib section, you might want to create a function that does plots for you if you want to make more of the same plot. So that's what we're going to do here. Just see an example of how we might create ROC curve plotting function. So first of all, we'll import matplotlib.pyplot. We're going to go as PLT, beautiful. And then we're going to go, call it nice and simple, plot ROC curve. It's going to take the false positive rate and the true positive rate. Then we're going to come here. We'll leave a nice doc string so it makes a bit of communicative sense. Plots are ROC curve given the false positive rate FPR and true positive rate TPR of a model. Wonderful, nice and simple. I'm going to go plot ROC curve plt.plot. We're going to pass it the false positive rate and the true positive rate, and we'll give it a color score. Got to remember that these libraries take American spelling. We go here, orange, and then label equals ROC for ROC curve, and then we're going to go plot line with no predictive power. This is going to be a baseline. You'll see it when the plot comes out. It'll make a bit more sense. That way we can compare our model to some other arbitrary model which just predicts nothing. 0, 1. Wonderful. And the color is going to be dark blue. Line style, we'll keep it dotted. Actually, this is only 2, so it looks different to our ROC curve. And the label is guessing. So this line you'll see when we plot is basically like our model was just guessing. And then we're going to go customize the plot. plt.xLabel. This is going to be the false positive rate, FPR. And then we're going to go plt.ylabel. You might be able to guess what this is. This is the true positive rate. This is because we got FPR as the X label and TPR as the Y data. True positive rate. And then we're going to go receiver operating characteristic ROC curve. Now, this is the type of plot you might give someone when they're asking for the ROC curve, right? So this is why I'm showing you this. Plot.show, and you'll probably also come along this sort of plot when you have a look at different classification problems online. They might use the ROC curve as an example of how the model's doing. We want FPR first, TPR. Beautiful. So this should work. Wonderful. What is going on here? We finally get to see what a ROC curve looks like. If we go to here, if the false positive rate is 0.6, the true positive rate is going to be 1.0. So the maximum score it can get is 1.0 up here. And so this model here, going from corner to corner, is guessing. Can you guess where the most ideal ROC curve might end up? If this is guessing, and our model is doing far better than guessing by getting about 80%, 85%, 82%, something like that. Can you guess where the most ideal curve will go? That's all right. If you can't, we're going to know is have a look at it. So before we do actually is let's have a look at the AUC score. We can do this from Scikit-learn import ROC AUC score. And so this is where the AUC comes into play from ROC. So when you hear area under curve or receiver operating characteristic, what is AUC score? And so we can do that. Let's just see it in action. This takes the test labels as well as the probabilities. Oh. So we can do Y probs. Oh, we need positives. There we go. So how did I know this? Again, docstring, Y true, Y score. Wonderful. And so what is this metric, you might be asking? Well, this is, remember, AUC stands for area under curve. And so if we were to calculate, take our curve, ignore this one for a second. Let's just get rid of that. So if we were to take our curve, this here, it's a bit of a jagged curve, but it is a curve. And if we were to measure the area, so shade in everything under here, shade in all of this, and figure it out, then we've got one across here. We're missing some space up here, so our area is definitely not going to be 1. Our score is going to get 0.84, so 0.849. Now the maximum score you can get, can you guess with an AUC score? So area under the curve. The maximum score you can get is 1.0. And so that means that the curve goes straight up here to this corner and straight across here to that corner. Now let's see it in action. So if we're going to go plot perfect ROC Curve, and AUC Score. So we're going to go FPR, TPR thresholds equals ROC Curve. Go Y test. Then we're going to go plot. We're going to use our function here, ROC Curve. See where it comes in handy because we want to plot multiple ROC curves. TPR, FPR, TPR. Let's do that. So this is a perfect ROC curve here. The area under the curve here, can you guess what it would be? We just discussed it. So perfect AUC score is ROC AUC score Y test, Y test. Now that's 1.0. And so in reality, a perfect ROC curve is very unlikely. That means you've got a perfect model. It's got no false positives. Everything's a true positive. If you saw a 1.0 here as a ROC AUC score, is that going to sort of maybe raise a flag to see if your model is predicting the right thing? The main details here that a ROC curve is predicting is a true positive rate versus a false positive rate. The main metric you can use to boil it down, rather than just being a curve, you can use the AUC score. So that's what you do to calculate a ROC curve if someone asks you to calculate a ROC curve for your model, and it's going to compare the false positive rate versus the true positive rate. So now we've seen ROC curves and area under the curve. Let's have a look at the next classification metric, or the next way to evaluate a classification model, and that is with a confusion matrix. Welcome back. And in the last video, we finished off saying the next classification model evaluation metric we're going to use is a confusion matrix. Now, if you're confused about the name confusion matrix, don't worry, it'll make sense after we go through it. So a confusion matrix, let's define it, is a quick way to compare the labels a model predicts and the actual labels it was supposed to predict. Now, in essence, giving you an idea of where the model is getting confused. Beautiful. Now again, if it's still confusing, don't worry, let's have a look. That's what we always do, right? We prefer to get hands-on. So from Scikit-learn, we're going to go from the metrics module, we'll import confusion matrix. And now we can create a confusion matrix by making some predictions. We've seen how to do this with the predict function. We're going to do that on the test data set. And then we're going to pass confusion matrix, the function confusion matrix, Y test, so the true labels, and the prediction. So this is the crux of what basically all evaluation metrics are doing, right? They're comparing the true labels with the predictions and giving us some insights on that comparison. And so if we hit Shift-Enter, we're getting an array back. What does this even mean? Just 4 numbers. Again, this is probably another thing that is easier to understand when it's visualized. One way to do so is visualize confusion matrix with PD crosstab. So let's see it in action. So we're going to go PD for pandas, crosstab, which is going to compare 2 different things. Y test, we want to compare the Y test labels. Again, just another comparison between the true labels and the predictions. Y test, Y preds, and we're going to pass it row names is actual labels. Column names is, can you guess? If not, that's fine. No, this is short for col names. Oh, and this will be row names. So we don't need that S there. This is going to be predicted labels. Wonderful. So, what is going on here? Well, because we are comparing the true labels versus the predicted labels, this is what our crosstab of the confusion matrix is showing us. So our predicted labels, where our model has predicted 0 or 1, and our actual labels. So here, the rows are the actual labels, and the columns are the predicted labels. So in our case, where the actual label is 0 and the predicted label is 0, we have 22 examples. And then where the predicted label is 1 and the actual label is 1, we have 24 examples. And now if we total all of these up before we check out the other 2, 22 plus 7 plus 8 plus 24. That's going to give us 61. And then if we remind ourselves of how many predictions we've made, there's 61. Why? Because there's 61 examples in the test set. Okay, so what are these two here? Right, so this is, let's read it out. So we got predicted label, where the model is predicted 1, but the actual label was 0. Ah, okay. So that's a false positive. So there's 7 of those. And now we have a predicted label of 0, but the actual label is 1. So that's 8 examples of that. So that's 8 false negatives. And so hence, this is where the confusion matrix or the word confusion comes into confusion matrix. These examples here, this diagonal, is where our model is getting confused, aka predicting 0 where the actual label was 1, or predicting 1 where the actual label was 0. And a confusion matrix, we look here, where the model got the samples right is on the diagonal. So this here. So if we come to our confusion matrix anatomy, now we're going to replicate this in the next video. This is our confusion matrix anatomy. We see correct here is a diagonal. So this is true positives, true negatives. False negatives is over here, so on the right side of the confusion matrix, and the false positives is down here. Why is it a false negative? Well, the predicted label is 0, right? And the model has, the true label is actually 1. And this is a false positive because the model is predicted 1, and the true label is 0. And we've seen this before, what a true positive, a false positive, a true negative, and a false negative is. So how would we replicate something like this, which is again a little bit more visual than our crosstab? One way to do so is with, let's make a comment here, make our confusion matrix more visual with Seaborn's heat map. Huh? You might be going, Daniel, what the hell is Seaborn? Well, if we go here, Seaborn heat map, this is what I do whenever I don't know something. We go Seaborn heat map. We look at Seaborn, you might be asking, what even is Seaborn? Seaborn heat map. Plot rectangular data as a color-encoded matrix. All right. Well, I'll give you the nuts and bolts. Seaborn is a visualization library that is built on top of matplotlib. And it's pretty relatively easy to use, but we're going to mostly just take care of the heat map function. So let's see it. So import Seaborn as SNS. And then we're going to go set the font scale of Seaborn, because it can be a bit smaller. Set the font scale, and we want sns.set. We want font scale. This is one of the easiest ways to visualize a confusion matrix other than a PD crosstab. So we're going to go create a confusion matrix. We're going to go confmat, short for confusion matrix, because we like to minimize the amount of keystrokes that we take. ytest, ypreds, pass it the test and predictions, just like we've done up here. And then we're going to plot it using Seaborn. sns.heatmap confmat. Oh, what? Module not found error. Drats, we can't use Seaborn. No, I'm kidding. So the reason why this module is not found is because you remember right back in the start when we created our environment using Conda? Well, when we did that, we didn't install Seaborn. And because Seaborn is built on top of matplotlib, we do have matplotlib, but we don't have Seaborn. We have pandas, we have Scikit-learn, we have Jupyter, but we're missing Seaborn. So how would you go about installing a module into your Conda environment, what we've got running in our terminal, right? So this is our Conda environment running in our terminal. This is what's serving up our Jupyter Notebook server. How do you think you would install it? So one way would be to go to terminal, start a new window. We might go cd desktop ml course, where my environment is stored, sample project. I'll zoom in here so you can see it. Sample project, ls. So we've got our environment here. And then if we go conda env list, wonderful. And then if we wanted to activate it, we could go conda activate. We want our sample project. I'll copy and paste that. Then I could go conda install Seaborn. That's one option. We won't hit enter because I'm going to show you the other option. I'm going to show you how you can do it right within a Jupyter Notebook. This is a little bit bonus tip, right? We're doing this during a classification model evaluation video. But because we want to use Seaborn, let's see how we can do it from within a Jupyter notebook. So this is something you might try whenever you get this module not found error. Say you come across some code or you come across a function that you want to use from a library you don't have installed. This is how you can do it from within a Jupyter notebook to install it into the environment so it's ready to go. So after running this cell here, we're going to be able to use this cell if everything works to plan. Yes, prefix. So what this is saying is we're importing sys. This is going to let us access our system, aka our computer. And then we're running this bang function, which is just a way of telling Jupyter to run a bash command. So as if we did the same command here, ls. Now if we run bang ls here, it's going to show us the exact same output, but just from within a Jupyter notebook. We'll get rid of that cell, we don't need it. And we're going to conda install, we're going to pass conda install yes. And prefix, we've seen prefix when we're setting up our environment. We're going to go sys.prefix. Prefix is just another word for path name, aka this thing here, path name. And then we're going to go Seaborn. So fingers crossed, if we run this cell, we should install Seaborn, and then we should be able to plot our confusion matrix using Seaborn's heat map function. So let's shift and enter. Oh, we're getting some loading. Beautiful. This is telling us what it's going to do. A newer version of conda exists, thank you. Package plan added / updated specs, Seaborn, yep. The following new packages will be installed, yep. Patsy, Seaborn, stats models. Preparing transaction, done. Tick, tick, tick. Moment of truth. Might take a little while to import. Oh, there we go. But it's not really offering much. Why is that? We go back to our keynote to see our confusion matrix anatomy. We want it to look a bit more like this, right? To get some numbers on there. Now, why isn't this offering that? Well, let's pause the video there. We'll continue on fixing up our confusion matrix in the next video, see how we can get some numbers on there. But take a little note of this one here. It'll be in the example code reference that you can use, but this is how you can install, how to install a conda package from a Jupyter notebook into the current environment. And then you just put the package over here. All right, so take a quick break. There was a lot to cover in that video. I'll see you in the next one. Welcome back. And in the last video, we saw how to create a confusion matrix with Seaborn's heat map function. But right now, our confusion matrix using Seaborn is not really offering much. Like it's blank. I'm better off using crosstab up here. But if we wanted to make it a bit more visual, what we might do is add some information to this and functionize it, because if we want to plot multiple confusion matrix, it's good to have it in a function. So let's make it plot confmat, and we'll pass it a confusion matrix with the variable name confmat, and then we'll put in a little doc string. Remember, we want to be great communicators here. Plot a confusion matrix using Seaborn's heat map. Something nice and simple. Again, we could upgrade this to say what actual confusion matrix is, but it's kind of intuitive. Anyway, fig ax, I want to set up a plot, plt subplots. We want fig size, we'll go 3 by 3. Ax equals sns dot heat map. We've seen this. We're going to pass it confmat. And then this is where we can add some information. So we want a not, short for annotate, equals true. We want to go here. This is a comment. Annotate the boxes with confmat info. Beautiful. And then we want a cbar equals false. Now these are parameters of the heat map function. You can see those in the documentation here, seaborn.heatmap, or as always by pressing Shift Tab there. Wonderful. And then we're going to add some communication. So plt.xlabel is going to be the true label, and then plt.ylabel is going to be the predicted label. Wonderful. Put a little semicolon there, and then we'll call plot confmat. How does this look? All right, we're getting some communication, we're getting somewhere, but why are our numbers appearing literally off the grid? Well, how would you figure this out? If you ran into this sort of problem, what would you do? Well, I'll tell you what I did. I went like this. I went Seaborn numbers not appearing in square on heat map. Something like that. There we go. SNS heat map top and bottom boxes are cut off. Now, this is one of the GitHub issues. With Seaborn, let's zoom in a little bit. With Seaborn 0.9.0 and Matplotlib 3.1.1, the topmost and bottommost row of boxes in the Seaborn plot are cut off. Ah, yes, 0's getting cut off there. So this is a big version of heat map, and so theirs is getting cut off just like ours. I see. All right, what can we do? This was a Matplotlib regression introduced in 3.1, which has been fixed in 3.1.2, still forthcoming. Okay, for now the fix is to downgrade Matplotlib to a prior version. All right, so there's a few fixes here, and so what I've done, we're not going to go through it all, but essentially that's the process I took, right? Was I just searched the error that I had, and then you come across resources like this and you read through them and you go, okay, there's some potential fixes, this might be my issue. In my case, my issue is that I'm using Matplotlib 3.1.1. But after a little bit more digging, I found a workaround that you can do without having to downgrade Matplotlib or wait for the update to come through. And that's fix the broken annotations. This happened in Matplotlib 3.1.1. By the time you try out this, right, this function may work perfectly for you because you'd be using Matplotlib 3.1.2 where the error gets fixed. But if not, this is a workaround, right? And that's what we are as engineers. We're looking for solutions to our problems. Not necessarily workarounds, but solutions to our problems. So this is ylim. So this is going to say bottom top ax equals get y limitations. So we're getting the limitations of our y-axis here. And then we're going to go ax.set ylim. We're going to go bottom plus 0.5 and then top minus 0.5. We can take out the semicolon here, put it here. So what is this doing? First of all, let's see it. Wonderful. So this is just saying, hey, set bottom and top to the current y limitations of our axes, and then reset them to be bottom plus 0.5, so it's going to move that number up. If we go comment out this, it's going to move that number up, and then it's going to bring this number down, or these two numbers down. So that's all that's happening in these two lines. And that was a fix, again, I found through a little bit of searching up something like that. Seaborn heat map plot numbers not appearing in the right way. Now, that's looking a bit more like what we used in our confusion matrix anatomy. Beautiful. And now that's looking like exactly something that you can start to share. You could even start to try and customize these labels here so that someone knows what 0 is, or put a little key here. So 0 is not heart disease, 1 is heart disease. You could customize this as much as you want, but that's essentially one of the best ways to visualize a confusion matrix. Now you might be asking is, why did we jump straight to Seaborn instead of using Scikit-learn? Surely they have a plotting a confusion matrix. And I thought the same thing too. But if we look at this, if we go from sklearn.metrics, import plot confusion matrix, then we go plot confusion matrix, pass it our CLF. So if we look at this, cannot import name plot confusion matrix from Scikit-learn. Why is that? So if we go here, Scikit-learn, plot confusion matrix, okay. And then we go down here. How's this happening? So from sklearn.metrics, import plot confusion matrix. Okay. And we see that they've used the function here. Now we click on this. sklearn.metrics plot confusion matrix. All right. So that's what we've done, right? We've imported it from here, from sklearn.metrics, import plot confusion matrix. Yet it still doesn't work. This is one of the caveats of using an open source library, right? Is that although Scikit-learn is incredibly helpful in offering us a bunch of different functions, and same goes for any other open source library, there are some cases where certain functions may not work, right? Like this. We try to import it, it doesn't work. So again, this is another example of where we've created a solution to our problem. If we couldn't use Scikit-learn's metrics function, plot confusion matrix, we build our own. We use Seaborn's heat map, or we could even just use Panda's crosstab. This is a prime example of putting on our engineering hat and figuring things out. But in essence, the main thing to remember with the confusion matrix is it shows you where your model is getting confused. If we go back to our anatomy, the correct predictions are going to be along the diagonal, and the false negatives and false positives are going to be on either side of that diagonal. So, with that being said, we've covered a fair few things with the confusion matrix. Let's have a look at one final classification metric, which is also really important, and that is called the classification report. We'll change this into Markdown, and we'll finish the video there. I'll see you in the next one. So the final classification model evaluation metric we're going to have a look at is a classification report. And now, really, a classification report is more so a collection of different evaluation metrics rather than a single one. So that's where the report comes from. It's going to report back of a number of different parameters evaluating our classification model. Let's see one in action. So from sklearn.metrics, import classification report. To do it, we just pass it some true labels, aka y-test, and some predictions. So once again, this evaluation metric is just comparing the true labels of our data versus the predictions that our model has made. So let's see what happens here. All right, there's a fair few things going on. We got precision, recall, F1 score, support, 0, maybe that's for the class 0, for not heart disease, 1, maybe that's for heart disease. If we come down, we got accuracy, 0.75, macro average, weighted average. What's going on here? Well, let's go to our keynote and have a look at our classification report anatomy. So over here, we see we've got the same thing, so just import classification report. We've done one on the test labels and the predictions. Some slightly different numbers here, what's in our notebook, but that's okay. So what's precision? Well, precision indicates the proportion of positive identifications, so aka the model predicted class 1, which were actually correct. Now, a model which produces no false positives has a precision of 1. So that's where we can see our precision scores. If the model produced no false positives, and we know that our model hasn't because we've looked at the classification or the confusion matrix and we've seen it confused on some examples and it's predicted them as false positives. So our precision scores are a little bit lower than 1. Now, the next one is recall. So recall indicates the proportion of actual positives which were correctly classified. Now, a model which produces no false negatives has a recall of 1.0. And again, we know from our confusion matrix that this isn't the case. So our recall is a little bit lower. Now, our F1 score, a combination of precision and recall. A perfect model achieves an F1 score of 1.0. Okay, so we see our F1 score is not 1.0, but it's still relatively high. Then if we go support, the number of samples each metric was calculated on. So we see here, so this means we look at this, 29. So if we look at that, that's for 0. And down here it's 61. So that means that these metrics here were calculated on 61 different samples. And these metrics along here were calculated on 29 samples which had the class label 0. And that this one is 32 with the class label 1. aka has heart disease. And so if you total these up, 29 plus 32, you get 61. Now, accuracy, we've seen that before. This is just the accuracy of the model in decimal form. Perfect accuracy is 1.0, aka our model is making predictions right 100% of the time if its accuracy is 1.0. Then we have a look at macro average. Now, what is that? It's short for macro average, as you may have guessed. So it's the average precision, recall, and F1 scores between classes. Now, the key here is macro average doesn't take class imbalance into, this should be effect, into or account. So pretend this is a count. So if you do have class imbalances, pay attention to this metric. Okay, so in our case, what is a class imbalance? Well, if you look at our example, we don't have class imbalances here. Why is that? Well, because we have relatively the same amount of samples with class 0 and class 1. Meaning, we've got about 50-50 split here. It's not exactly 50-50, but it's not like we have 60 examples of class 1 and 1 example of class 0. So we've got about 30 in each. So if you did have class imbalances, you really want to check out your macro average. Now, because our example, the classes are relatively balanced, that's why the macro average and the weighted average, short for weighted average, AVG, the weighted average is the precision, recall, and F1 score between classes. Weighted means each metric is calculated with respect to how many samples are in each class. So this metric will favor the majority class. For example, will give a high value when one class outperforms another due to having more samples. So this is why that our values here are quite similar, because we have balanced classes. Now you might be thinking is, what kind of situation would it be that these values would be out of whack, right? Like, where would this happen? And you might also be thinking, we've learned a whole bunch of different metrics here. We come back to our notebook, we've gone over classification reports, we've done confusion matrix, we've done accuracy, we've done area under ROC curve. So when should I use each of these? So now we've kind of gone through them, it might be tempting to think, well, why don't I just ditch all these other ones that I really am having kind of trouble grasping and just use accuracy? Well, let's have an example. Let's see when other metrics come into play, and maybe you shouldn't just use accuracy, because this is a trap that I got caught in, right? When I first started building classification models, I was like, yes, my model is getting 90+% accuracy. It must be a great model. Let's see a scenario. So for example, let's say there were 10,000 people and one of them had a disease, and you're asked to build a model to predict who has it. All right? So let's actually do that. Let's code this up. So this is where precision and recall become valuable. And in fact, all the metrics in our classification report become valuable here. So disease true. So there was 10,000 people and one of them had a disease. So what we might do is create a NumPy array of 10,000 people. And then we might change one of these. If I can spell disease. So disease 0th index equals 1. So there's only one positive case. Then if we come down here and say our model predicted or disease preds equals NP zeros 10,000. Now this means model predicts every case as 0. All right. And then what we're going to do is create a PD data frame so we can visualize this. Classification report. What if that's what our model did, right? This is what's happening here. Disease true. So there's only one positive case, 1 in 10,000. And we build a model, and our model predicts that every single case is 0. So it misses the one prediction. What would happen if we build a classification report? So we go disease true. We go over here. Disease preds. We want to pass this little parameter so it fits nicely into our data frame. So output dict equals true. All right. So what's happening here? If we look at this, this is just another format of this classification report up here. If we didn't do this, it would error out. So this is just to visualize what's going on. True. So this is a prime example, right, of where you want to use another metric other than accuracy, is when you have a very large class imbalance. So in our case, we have a massive class imbalance because in our original data set, disease equals true, there's only one example. So only one example of where the label would be 1 and everything else is 0. We've built a model that just predicts 0 for every case, right? Because it's only one sample, so it's really hard to learn that there's a pattern there for this one particular case. And so what happens is, if we were to measure just accuracy on our model that has predicted 0 for everything, it comes out with an accuracy of 0.99, or in other words, 99%. And so ask yourself, although the model achieves 99.99% accuracy, is the model still useful, right? That's where we look at these other metrics, such as the macro average. That's where we can see, okay, our model's falling down here on the precision. It's actually getting 0 precision for class 1, which makes sense because it didn't even predict class 1. And here, it's getting basically 100% on class 0 because it has only predicted class 0. So this is a kind of use case scenario of where you want to make sure that you're using a wide spectrum of evaluation metrics for your classification models and not just accuracy. And now we've only just touched on some of the metrics that you can use for evaluating a classification algorithm, but there are a few more. So if you want to have a look at more, so we go here, model evaluation, Scikit-learn. We'll look at the documentation. If you come in here, this is a little bit of extracurricular, is to have a look at this section here. So all I've done is gone into the Scikit-learn documentation for model evaluation. We come to classification. We can see a few here, the ones that we've covered. And so the ones that we've covered are probably the bare minimum that you want to use, right? So accuracy, area under the ROC curve or AUC, confusion matrix, and classification report. So keep those in your tool bag, and if you need more, be sure to refer to the documentation. So that's going to wrap up our classification specific evaluation metrics. Let's dive into the next section where we'll have a look at some more specific regression model evaluation metrics. Alrighty then. So now that we've covered some classification metrics, and by the way, I've just put this little paragraph here so you can check it out of when to use different classification metrics, just to kind of break it down in 5 dot points for you. But now we're going to cover some regression model evaluation metrics. And put your hand up if you're ready. I'm holding my hand up too, don't worry. Alright, so let's put in a little heading. 4.2.2. Regression model evaluation metrics. So as always, the documentation is ready to go. So we've got this here. I might put this in here. Another link here. Model evaluation metrics, documentation. Now, I don't want you to be scared like reading the documentation like I was when I first started. If you read this, and there may be a few times where you go through it and you go, wow, you see something like this. You see a bunch of different words here that you don't really understand. You look at a bunch of different examples, you're reading this, and it's like kind of confusing. Don't worry. That's exactly how I started, but after a little bit of practice, after implementing the code like we're about to do, that's why I'm such a big fan of implementing code, I started to understand a little bit more, started to understand about what I needed to use. So, speaking of what we need to use, for regression, we're going to look at 3 different ones. And these are 3 of the most common, 3 of the most useful. And the first one is R squared, pronounced R squared, or coefficient of determination. Beautiful. And the second one is mean absolute error, which is also known as MAE. And the third one is mean squared error, which is also known as MSE. Wonderful. So now we've got that, let's bring back our regression model. So from sklearn.ensemble, import random forest regressor. Wonderful. We'll set up a random seed so our results are reproducible. Then we'll get our X, which is the feature variables from our Boston data frame. So we want to just drop the target and the axis equals 1. The labels are the target column, or is the target column. Wonderful. And now we'll split our data into train, test, using train test split, passing it X and Y. Wonderful. And then what we're going to do is instantiate our random forest regressor, because we want to build a regression model so we can evaluate it. Wonderful. Model.fit, X train, Y train. Now this is going to give us a warning because we haven't set number of estimators to be in 100. And we're going to run this. Invalid syntax. Classic. From, oh no, import. There we go. Oh, Boston DF is not defined because they've got typos. There we go. See, this is what happens, right? When you're writing code, don't expect to get it right the first time. You're going to get errors. So always remember, if in doubt, run the code and then go back and fix the errors when you need to. Score, we've seen this, y-test. Wonderful. And so now R squared can be calculated using, well, actually, where am I getting R squared from? So this is, remember, regression metric number 1. We'll put it here in bold so we know that we're looking at R squared. So that is the default metric here, right? And so the coefficient of determination, R squared of the prediction. Okay, so if we wanted to figure out what exactly R squared was, where can we do that? Maybe we go to Wikipedia. In statistics, the coefficient of determination, denoted R squared or R square, and pronounced R squared, is the proportion of the variance in the dependent variable that is predictable from the independent variables. These are pretty complicated definitions. Well, after doing some research, I created one of my own, right? This is what I'd like you to do, right? If you ever come across something and you see the formal definitions of them, when you look at them from first glance and you're like, this is kind of confusing, is to go in and search and find a way to explain things in your own words. So in my own words, an R squared value compares your model's predictions, here, what R squared does. Compares your model's predictions to the mean of the targets. This is the values of R squared, can range from negative infinity, so that's the lowest possible, that's a very poor model, to 1. Now this is where I love having an example, right? For example, if all your model does is predict the mean of the targets, its R square value would be 0. And if your model perfectly predicts a range of numbers, its R square value would be 1. Whew. If ever you come across something you don't understand, research it, look at different sources, go to Wikipedia up here, read the documentation, right, see an example, but then most importantly, implement it yourself. So I want you not to take my word for it here. For example, if all your model does is predict the mean of the targets, its R squared value would be 0. And if your model perfectly predicts a range of numbers, its R squared value would be 1. So as I said, don't take my word for it, but let's see this in action. So from Scikit-learn, metrics, import, this is another way to calculate R squared, is you could just go R2 score from the Scikit-learn metrics. And then we go here, and we want to fill an array with y-test mean. So the mean values from the y-test data set. So we can do that pretty easily with NumPy. So y-test mean equals np full, so meaning full array of len y-test. So we want it to be the same length of y-test. And then we're going to fill it with y-test.mean. So does that make sense? Beautiful. So if we look at y-test.mean, all this array is an array full of those values. Boom, 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 boom. And so remember what my example said. If all your model does is predict the mean of the targets, its R squared value would be 0. Okay, well let's test this out, right? Because that's what we do. We're engineers, we test things out. R2 score, y-test, we're going to compare the true labels. All our model did was predict the mean. So very simple model. Oh, it gets an R2 score of 0. Well, okay. And now the second part of that example was, and if your model perfectly predicts a range of numbers, its R squared value would be 1. Okay, so if our model got the exact same predictions as the test values, its R squared value would be 1. So let's see that. We can do this one pretty easily. Y-test. Now, if it got the exact same predictions, if it predicted the y-test labels perfectly, it would end up with a score of 1. So what does this tell us? Well, this gives us a quick indication. This score function, which implements the coefficient of determination, aka the R squared, gives us a quick insight into how closely our model's predictions are to perfect predictions. So, of course, 1.0 is perfect. And so we got 1.0, we saw that here. And if it was predicting nothing but just the mean, it would get 0. And it says here that the value can range from negative infinity. Well, what this means is that if our model predicted completely off the radar, this value can actually go negative. So the mean is actually an okay prediction compared to something that was just predicting all zeros, right? Now that we've seen R squared, it kind of gives us a quick insight into how well our model may be doing, but it doesn't really tell us how far off each prediction is. So to do that, we're going to use mean absolute error. So we'll look at that in the next video. Welcome back. So in the last video, we covered R2 score. And so in this one, we're going to look at mean absolute error. So let's come down here. We'll create a little heading. Mean absolute error, aka MAE. Now again, we could always look up what mean absolute error is, but what we're going to do is check it with the code first, and then we'll look into it. How do we calculate it? Mean absolute error. You might be able to deduce from its name what it actually does. If not, that's all right, we'll look into it. Import mean absolute, nearly did square error, that's going to be the next one. To evaluate it, we need to make some predictions because remember, evaluation metrics are always comparing truth labels to predicted labels. So we'll predict on the test data set. We'll go MAE equals mean absolute error. And we're going to compare y-test, which is the truth labels that we made up here, y-test, to our predictions, which is what we've just made here. And then we're going to have a look at MAE. Okay, that wasn't too hard. But 2.12, what does that mean? Well, again, this might be a little bit easier to visualize, right? So we might create a data frame. Side by side, we're going to pass it data equals a dictionary, and we're going to have actual values versus what we want here is predicted values. We'll go y preds. Wonderful, and then we'll have a look at DF. So what do we have here? Well, this is the truth labels. This is what our model has predicted. So we can see 23.6 is 23.002, okay, 32.4, 30.8, 0.2. Looking at these, right, and then looking at this number, can you think about where this number might be coming from? That's all right if you can't. What we might do is add another column that may add a little bit of clarity. Equals, and we're going to do df predicted values. So this is a column we're creating for the differences, right? So the difference between our predicted value and the actual values. There we go. Then we'll view df again. Differences. Okay, so we see that this one is minus 0.6 or so. This one is minus 0.5, and this one is 3.1, so it's a fair bit off here, and this one was really off, right? It's minus 4.87. Okay, so now you might be starting to get an idea of where mean absolute error comes from. If not, mean absolute error, it's formally defined as the average of the absolute differences between predictions and actual values. And so it gives you an idea of how wrong your predictions are. So what we might do is write that here. So MAE is the average of the absolute differences between predictions and actual values. It gives you an idea of how wrong your model's predictions are. And what it means by absolute is that it would turn these values positive and then add them all up and then take the mean. And then that's going to give us this number. So basically, what this is saying is that on average, every prediction our model makes is going to be on average plus or minus 2.12 away from the actual value. And you can kind of see that, right? Some are only 0.667 away, but others are more than 2.1. So this is 2.89. And this is negative 3.794. And you could keep going throughout all the 102 rows and figure out this figure manually, or you could just take the Scikit-learn implementation's word for it. So what we're going to do next, that's covered mean absolute error. We're going to have a look at mean squared error. Alrighty, now we've covered mean absolute error. We're going to have a look at mean squared error. So we'll go here. Actually, we'll make a little heading. as usual, because we're keeping our notebook nice and clean. So mean squared error. Wonderful. And then we're going to go mean squared error. Now you might, based off what we've looked at with mean absolute error, you might be able to deduce how we might calculate mean squared error. If not, again, perfectly fine. So if we come down here, so from Scikit-learn, .metrics, import mean squared error. Wonderful. And so we're going to do it basically in the exact same way. So MSE equals mean squared error, except this time, instead of using absolute, we're going to be using squared. Then we're going to take the Y test labels, and because we've already made predictions up here, Y preds, we could make them again, but we might just reuse the values here, Y preds. Actually, for completeness, what we might do is just the Y preds equals model.predict, and we're predicting on the X test data because we want to compare our predictions to the Y test data. Then we're going to have a look at MSE. 9.242. That's a little bit higher than what we got with mean absolute error. Well, that's because MSE, or mean squared error, I should put MSE in here, right? Because there's so many acronyms these days. MSE will always be higher than mean absolute error because it squares the errors rather than only taking the absolute difference into account. So if we come up here and have a look, this data frame would be the exact same here. So what mean absolute error does is it takes these values and it turns negatives into positives, adds them all up, and then finds the average of it. What mean squared error does is it takes these values, squares them, then adds them all up, and then finds the average, hence the mean squared error. So that's why the squaring part, squaring these numbers, will lead to a higher number here. Actually, we might just do it. So let's see if we can. Calculate MSE by hand. Now this is dangerous, right? We're going off the record here. Calculate MSE by hand. So all we have to do is take the differences here. So actually DF differences, we need to square that. Actually, you might do here. So MP, is it MP square? Yeah, MPSQ square DF differences, and then should be able to call the mean on that. So actually, let's put that in brackets. Can we do that dot mean? Right. Squared equals that. What does squared look like? Okay, so this is going to take this column here as squared. Now, to calculate the MSE, we just need to take the mean of squared. Beautiful. There we go. See? That's how we calculate the mean squared error. That's it, right? We've covered mean squared error, we've covered mean absolute error, and we've covered R squared. Now, the next logical question is, and even if you aren't asking it, is which regression evaluation metric should you use? So we look here, we'll come back to the keynote. So R squared is similar to accuracy, right? It gives you a quick indication of how well your model might be doing. Generally, the closer your R squared value or coefficient of determination value is to 1, the better the model. But as we've seen before, R squared doesn't really tell us exactly how wrong our model is in terms of how far off each prediction is. For that, mean absolute error gives a better indication of how far off each of your model's predictions are on average. So that's when we saw this one here, right? This is how we saw, on average, each of our model's predictions is about 2.12 away from what it actually should be, whether that's positive or negative. And so we come back here. Now, it can get a bit confusing which to use between mean absolute error and mean squared error. Well, because of the way mean squared error is calculated, we saw that by calculating it by hand. We squared the differences and then took the mean, right, instead of just taking the absolute differences. Because of how MSE is calculated, squaring the differences between predicted values and actual values, it amplifies larger differences. So you could imagine if we had a difference of, say, 10 and we squared that, right, that's going to be now a difference of 100 and we're taking the average of that. So let's say we're predicting the value of houses, which we are. You want to pay more attention to mean absolute error when being $10,000 off is only twice as bad as being $5,000 off. So that makes sense, right? But pay attention more to mean squared error when being $10,000 off is more than twice as bad as being $5,000 off. You might think, well, it's not really if I double $5,000 to $10,000. So this is kind of another way of saying is that when bigger errors are bigger than smaller errors, right? So if we're $10,000 off, and that's way worse than being $5,000 off, we want to look more to mean squared error. Long story short, a little tidbit here is for regression models, you want to minimize mean squared error and minimize mean absolute error while maximizing R squared, right? So does that make sense? Minimize mean absolute error, minimize mean squared error while maximizing R squared. Whew. Now that we've covered a handful of some of the most useful and common regression metrics, we come back here, we see that there's still a fair few more that we could have done, right? So that's a little challenge to you, is to dive into model evaluation metrics, but the ones we've gone through are more than enough to get started. You might be thinking, hold on, we haven't even used the scoring parameter, which is what we talked about 5 or 6 videos ago. Well, now that we've covered some of the, as I said, some of the most common and useful regression and classification metrics, we can finally take a look at the scoring parameter, which is what we'll do in the next couple of videos. Whoa, we've really covered a bunch, but we haven't even touched the scoring parameter. And as a refresh, the scoring parameter is one of the second ways that we can evaluate a model, right? So the scoring parameter is used with model evaluation tools that use cross-validation, such as model selection.cross-val-score. We've seen that one before. And model selection.grid-search-CV. Now, we haven't seen that one before, but what we're going to do is check out how we can use the scoring parameter with cross-val-score. Before we do so, let's set up a little heading. Let's remind ourselves finally using the scoring parameter. And I know there's a lot to take in, right? And I don't expect you to know everything right straight away. It's going to take a little bit of practice, a little bit of time, a little bit of effort for these things to start to sink in, right? So here we go, finally using the scoring parameter. And speaking of practice, it's one of the reasons why we keep practicing writing out, building machine learning models and splitting our data. So for model selection, we're going to import cross-val-score because that's where we can use the scoring parameter. And then we're going to import our random forest classifier. Import random forest classifier, yep. And then we can go np.randomSeed. 42, our favorite number. Again, you could use almost any number here. I actually really like the number 7 too, but 42 will do. X equals, we'll set up our X data, heart disease, .drop. Target axis equals 1, beautiful. Y equals heart disease target, there we go. And now we can set up a classifier. And we're going to use, of course, random forest classifier, our favorite, the warhorse of machine learning. We'll set number of estimators to be in 100 so we don't get that pesky little warning that we've been getting. And we'll do that. Beautiful. So we've instantiated our machine learning model. It's ready to be fit. So we can do that here. MP random seed, we'll do it again. And we'll go CV ACK. Why are we doing CV ACK? Well, we'll see in a second, right? Cross-val-score, CLF, X, Y, and then we'll use 5-fold cross-validation. CV ACK. Wonderful. It's going to train 5 models, evaluate them on different test sets, and then, of course, we could take the mean of this. So why don't we do that? We'll go cross-validated accuracy. So we could go print F. The cross-validated accuracy is, need some spaces here, Daniel, come on. The mean, NP mean, CV ACK. And then we're going to take that to, we'll only use times 100 and 2 decimal places. And we'll put a little percentage sign on the end. And we need a final string delimiter. Beautiful. So now the cross-validated accuracy is 82.48%. Now we've seen this before, right? We've seen this line, we've seen this line. And the reason why is we're using this is because by default, the model, it uses accuracy, cross-val score, because in essence, this is scoring equals none. So this is going to produce CVAC. And then if we go here. So now if we just copy this, right? Actually, what we might do is just test it out by only changing one thing. So if we take this, we'll copy this line just to prove it. This is where the scoring parameter comes in. So we can use accuracy here. All we're doing is changing none to accuracy. Because remember, our random forest classifier, by default, uses mean accuracy. So remember, the scoring parameter, when left to none, uses a classifier or estimator's default parameter from score to evaluate using cross-validation. So we'll get rid of that. Now, all we've done is we've changed scoring equals accuracy. And then we're going to take this line here. We'll just copy this. And if this is true, right, if I'm not telling lies, it should print out the exact same thing here. Because CVAC equals cross-val score, CLF, XY, CV equals 5, scoring equals accuracy should be the same as this. Let's see it. Oh, you know why it was different? It was because we forgot our NP random seed. Yes, there we go. Boom. See, that's another reason highlighting the use of NP random seed, right, is making our experiments reproducible. All right. Now, to see another metric, this is where the scoring parameter really starts to shine. How about we use precision? So CV, precision, to evaluate our classification model, cross-val score, because remember, precision is one of the metrics that we can use to evaluate our classification models. Now, all we're going to do is change scoring equal to precision. Beautiful. And we'll see what CV precision is. Wonderful, but we probably take the NP mean. Beautiful, so 0.82 on the precision front. We might do here, precision. Now, how about recall? So we'll go CV recall equals cross-val score, CLF, X, Y, CV equals 5. Scoring, can you guess what the scoring parameter might be equal to here if we wanted to calculate recall? Not to worry if you can't. We'll do it here, recall. And then we want NP mean to get the cross-validated recall. Wonderful, 0.84 recall. And now how about for F1? How about we do that? Yeah, why not? CV F1 equals, remember, F1 is a combination of precision and recall. X, Y, CV equals 5. Scoring equals F1. We want NP mean dot CV F1. Wonderful. There we go. Okay, now we've done some classification metrics here. How about our regression model? Well, why don't we make a regression model and check it out? Okay, from Scikit-learn.model selection, import cross-val score. So we want to cross-validate our regression model's predictions. So from Scikit-learn.ensemble, to get all the benefits that cross-validation offers, random forest regressor. Look at us go, typing machine learning code like it's nothing. Go NP random seed 42. We'll create our X data. So Boston DF. Yes, drop target axis. Can you guess what axis? Axis equals 1. Yes, equals Boston DF. So this is Y actually. Target. I'm getting ahead of myself. My voice can't keep up with my coding. Model equals, which is very unusual for me actually. Random forest regressor. We'll set n estimators again to being tab autocomplete to being 100. Wonderful. And now, do you remember what the default metric is for score for a regression model? So if we do model.score, the default evaluation metric is returns the coefficient of determination, R squared of the prediction. Alrighty. Well, let's check it out. So NP random seed, and then we're going to go CV R squared equals cross-val score, model this time, X, Y, CV, 5-fold cross-validation. Let's do scoring equals none, right? And then we're going to CV R squared. Then we're going to copy this exact code Boom. And because remember, cross-val score uses the default evaluation metric in the score function if set to none. So if we just change this to be R2, what do you think is going to happen? Because this is short for R squared, right? So if we go here, boom, we get the same values. Look at this. Now this is pretty drastically different, right? So we got over here, this is 0.85. This is what I was talking about getting that lucky split. So cross-validation, on this one, it's done pretty well, so 0.85. But on this split, it's only done 0.25. So if we got here, if we did the MP mean, it's 0.622. Now that's quite a bit different to the first R squared score we saw just using the score function. Well, let's keep going. Let's not stop there. How about we do mean absolute error, because that's another regression metric. So let's try it out. So CV MAE, we'll put it in here. Mean absolute error. Wonderful. CV MAE equals cross-val score. We'll pass it our model, which is a random forest regressor, X, Y, a CV of 5. Scoring is going to be, what might this be? We might type in, we'll guess this string, mean absolute error. Let's just see them all laid out, because that was pretty cool to see with our R squared score, right? Just to see how different they can be across 5 different splits of data using cross-validation. Key error, mean absolute error. Now, why is that? And I'll tell you why. It's because we need neg in the front here. Oh, and you might be asking again, why neg? But I'll show you that in a second. Okay, so that's interesting. So if we come up here, we can tell why it means neg is because all scorer objects follow the convention that higher return values are better than lower return values, right? So that's a key point to remember here. This is in the documentation. All scorer objects follow the convention that higher return values are better than lower return values. So if we come down here, this is why we have, might zoom out because that's looking a bit too big. This is why we have neg mean absolute error. I'm looking back in our notebook. See, these values are all negatives. And the reason being is because all scorer objects follow the convention that higher return values are better than lower return values. So that means because these are negative, the higher these are, so the closer they are to 0, it's better than the lower they are. So these are pretty low, so again, our model isn't perfect. But you can see the variations in the mean absolute error values, just like we had in the R squared values, is that some splits, right, because we did 5 splits, are offering negative 0.212. We saw 2.12 up before. But other ones we're getting a much higher one here, so negative 3.8. So this is where cross-validation really comes into play, right? Is figuring out, okay, are we just getting a lucky split on our model and training it on some easy training data to understand? And then evaluating on the test data set, we might be going, if it's a lucky split, it might be getting metrics that aren't really congruent with how the model is actually performing. So let's finish this off. We're doing mean squared error. And now I bet you can guess how to do this one. So CV MSE equals MSE for mean squared error. Cross-val score, we'll pass it the model. And then we'll do X, Y, and we'll do CV equals 5. Scoring equals. Now, if we had to do neg mean absolute error, what do you think it is for mean squared error? And if you guessed neg mean squared error, you would be 100% correct, which is the opposite to what our model is. CV MSE. Shift and enter. And again, we're seeing some quite a wide range of values here, right? So we go from negative 7.77 right up to the highest one here is negative 46.2. So we could take the mean of these to see what it looks like across 5 different splits. So negative 21.5. So that's a bit different again to our previous value when we weren't using cross-validation, right, of mean squared error, is 9.24. So naturally, if we're looking at these evaluation metrics and we're starting to see, okay, we want to get better metrics, you might be starting to think is like, how can we start to improve these metrics? How can we make them better? And we're definitely going to look at that. But finally, to finish the evaluation metrics section off, we're going to have a look at the third and final way of evaluating a model, and that is using metric functions. Spoiler alert, you've seen some of these in action before. Just to make sure we're evaluating our models correctly, we're going to have a look at those. So take a little break. We covered a lot in this video. Try adjusting the scoring parameter yourself. Don't forget, if you're getting different values, you might be using a different seed every time. And I'll see you in the next video. Alrighty, let's finish up this section on evaluating machine learning models. So we can do so by tackling the third and final way to evaluate a machine learning model, metric functions. So in essence, we've kind of already covered this because all of the metrics we've previously seen have their own function in Scikit-learn. Let's see what I mean by this. So using different evaluation metrics as Scikit-learn functions. 4.3, wonderful. So to do so, for classification, we had accuracy, we had precision, we had recall, we had F1. And then for regression, we had R squared, mean absolute error, and mean squared error. All right, so let's do what we always do and see the code first. And then we'll talk through it. So from Scikit-learn, import metrics, and we're going to do a full example as we always do, right? Because that's what we like to do. We like to be complete with what we're working on. Precision score, recall score. You might be able to figure out what the one is for F1 score. Oh, typed it a bit too quick. So from Scikit-learn, we'll also import our model, because what we might do is create a section here. We might go classification, evaluation, functions. Now again, this section here is just another way to do what we've done before. So ensemble, but it's good to practice. It's always good to practice. Random forest classifier, and then we want scikit-learn.model selection, import train test split, mp.randomSeed, 42, lovely, x equals heart disease dot drop. We can almost write this in our sleep now. Y equals heart disease dot target. And if you can't, that is more than okay, right? The only reason I can write this sort of out is because I've had a fair bit of practice with it, and you'll be the same too. If you're starting out now, you might be looking at all these functions, all this code, and going, holy goodness, there is so much to remember. But the beautiful thing is that it's here, it's available for you. You can run it in Jupyter Notebook, and you can practice as much as you like. So really, your only roadblock is just putting in the work and practicing learning. But don't forget, learning something new, especially machine learning, takes time. And it's not going away, so you got plenty of time. So what we're doing here, we've seen this code before. Importing some metrics, specifically accuracy score, precision score, recall score, F1 score. And we're importing a model, and we're importing train test split. We're splitting our data into X and Y. We're splitting it into train and test sets. We're instantiating a random forest classifier and fitting it to the training data. Beautiful. Writing machine learning code. We'll make some predictions. And then we'll go Y preds, because remember, what is an evaluation metric doing? If you said comparing our model's predictions to the truth labels, to the actual labels, you would be correct. Evaluate the classifier. So now what we're going to do is we're going to take advantage of these inbuilt functions here. Right? We could use score, we could use a scoring parameter, but we've already covered those. This is using Scikit-learn functions. So evaluate the classifier. What we'll do is we'll print out something nice, maybe. Classifier metrics on the test set. Wonderful. And then we're going to print out, we'll do an F string. Accuracy is going to be, we'll use the accuracy score function on Y test and Y preds. Wonderful. And then we're going to times that by 100, so it comes out in a nice, neat percentage, because I prefer that, or we all prefer that, than the decimals. Maybe you don't. Then we got here, we're going to go precision. Now, again, we could functionize something like this. We probably will in a future video, but just for example's sake, we'll type it out. We'll practice typing it out. That can stay like that. Oh, it needs the end of a string. There we go. Now we're going to do recall. How would you do this one? If I start you off with the F string, that's all right. We'll keep going. So recall score, Y test. Remember, just comparing our predictions to the test labels, to the truth labels. And then finally, we're going to go F1. So this is something you might do, like if you're reporting to your colleague or to your boss or to your manager or something like that, or to the greater public, like how your model is doing, you might give them all these different evaluation metrics so they can start to understand, okay, the accuracy is a certain thing, but the precision is this, so they have an idea of how many false positives there are, and the recall is this, so they have an idea of how many false negatives there are, and then the F1 is kind of a combination between the precision and recall. So we'll hit Shift and Enter. Voila! Now we've taken advantage of the third method of evaluating models, and that's by directly using functions such as accuracy score, precision score, recall score, and F1 score. If we come up here, the documentation, this is a metric function, right? Classification metrics. Here we go. There's a whole bunch more there if you want to check them out. But these are some of the main ones that we've covered, and the principle is still the exact same for the rest of them. And so if we come in here, we're going to do regression evaluation functions. Turn that into Markdown. So same thing again. You could almost do this yourself, I reckon. And if not, don't worry, we're about to type it out. But how would you go about it? If we look at our classification evaluation functions, what you might do is from Scikit-learn.metrics, import some regression functions, then import the regression model, then import this, train, test, split, create the data, split it into training and test, instantiate your regression model, make some predictions, and then evaluate them. But this time, instead of evaluating a classifier, you're evaluating the regression model using regression metrics. But just for completeness, let's type it out again. Metrics import R2 score. Wonderful. Mean absolute error. Now we've seen these before. Mean absolute error. Mean squared error. Beautiful. Scikit-learn.ensemble. Import random forest regressor. So this is the kind of workflow you might do for your own problems, right? If you're working on a regression problem, you might have some sort of import statement up the top of your notebook like this. Import train test split. In our case, we've already got our data in a data frame. You may have some more lines of code getting your data to a proper data frame. Oh, we almost forgot MP random seed. So that you actually don't need a random seed. I just like to have one, and you'll see them all over the place, just so if you run the results the same as what someone else was getting. Target axis equals 1. Y equals Boston DF. Target. Beautiful. So, and another reason, the random seed, right? So if I ran these cells, and then you took this notebook as the resource for the course, and then you wanted to compare your results to mine, without the random seed, they'd probably be different because all of the randomness in this notebook, such as train, test, split, randomly splitting our data into training and test sets, would use different samples for each. And so we'd get different numbers, and that would cause confusion, which is not what we're about, right? If we're all about communicating what we're finding. So we're instantiating a model here. So random forest regressor. Wonderful. I'm going to go model.fit. We're going to X train, Y train. Beautiful. Make predictions using our regression model. Model.predict X test. Yes, yes, yes. And now evaluate the regression model. So we're going to go here, print regression model metrics on the test set. Again, you could functionize this to pass it your regression model as well as some metrics, but we're just going to write it out here just for good practice. R2 score, Y test, Y preds. Wonderful. Then we just need to end the string. We can do the same for mean absolute error. So MAE equals mean. We'll tab complete that one. Of course we will. ypreds. Wonderful. And then we go print f MSE mean squared error, comparing it, predictions to the actual labels, finishing off with a string. And boom, oh, we got an error. Of course we did. And this is going to give us a warning because our n estimators is not equal to 100. And what is our other error? Found input variables with inconsistent number of samples, 102. What has happened here? 102 y-test y-preds versus 61. Well, you know what it was happening? It's 61 is the number of... here we go. There we go. You know how I knew that? It's because if we go up here, and if our classification problem, if we go len ypreds before we instantiate our regression problem, it's 61. So because we didn't set ypreds here, right, previously, this was just this. It was using ypreds from above. That's where I got caught out from using the same variable names throughout the notebook, right? Ideally, we'd have different variable names for our classification and regression problems, but just to illustrate purposes, this is usually called ypreds or something of the like. And there we go, regression model metrics on the test set. Now, we've seen similar metrics before. What can we do now? Well, we've covered a whole bunch, right? And the reason being is because evaluating a machine learning model is paramount, right? It's one thing to train one, but then again, there's nothing worse than training a machine learning model and optimizing it for the wrong evaluation metric. So keep the metrics and evaluation methods we've gone through when training your future models. Make sure you keep them in mind, go through them, and have a little read here. This is probably the most important section that you'll read of the entire Scikit-learn documentation. But after you've done that, you'll naturally probably start to ask, is that how do we improve these numbers? How do we make them better? They're kind of stagnant. We've been using a random seed and we've been seeing just the same numbers for accuracy, precision, recall, and F1 over and over. And same with R squared, MAE, and MSE. So in the next section, that's what we're going to cover. So if we look back at our list, what we're covering, number 5, we're up to improving a model. All right, so take a little break. Have a look at the Scikit-learn documentation for metrics and scorings, quantifying the quality of predictions. You can find it by just going to this URL here or searching sklearn evaluator model. But otherwise, get ready for the next section. We're going to see how to improve our models. Alrighty then. Now that we've figured out different ways to evaluate our machine learning models, your likely next question is, how can we improve upon these metrics? And that's what we're going to cover in this next section. Section 5, which is improving a model. So let's make a heading here. We'll go 5, improving a model. Now, the thing to remember here is usually, actually, more often than not, the first predictions you make on a model are not its last, right? And these first predictions are often referred to as, let's write this down, first predictions equal baseline predictions. And first model is often referred to as baseline model. What you'll try to do is, as you go on, is once you've made some first predictions and evaluated them, and once you've built a first model, like a baseline model, you'll try to improve upon that. So AKA, improve your predictions and improve your model. And now, how can we go about that? Well, there's two main ways. The first one is from a data perspective. You'll ask questions like, could we collect more data? Because more data means that a machine learning model may have more of a chance to learn patterns within that data. And there's a saying in machine learning is, generally, the more data, the better. And it's similar to how if you were to practice something, right? And if you do a bit more practice than usual, you might get a little bit better at that thing. Maybe not exorbitantly better, but certainly if you do 10 sessions of practice, you'll probably be a little bit better if you do 1 session of practice. Same thing goes with machine learning, right? If there's 10,000 examples rather than 1,000 examples of something, chances are, if there's patterns in that data, the machine learning model will pick them up. And the second one is, could we improve our data? Now, this is if you had, for example, in our car sales problem where we're using the make, the color, the odometer, and the number of doors to try and predict the sale price of a car. Now, if you were given that information, it would be kind of hard to predict the sale price of that car, right? So what you would search for here is maybe more features about each car. So you would have more information about each sample. So rather than just more samples, you've got a more depth of information within each sample. And then what we're going to be focusing on is from a model perspective. And this asks a question like, is there a better model we could use? So if we look at the Scikit-learn machine learning map, we've seen an example of this before. So for example, when we followed it through and we started off with a linear SVC and we figured out, oh, those results aren't too good back in our classification problem. So then we went up and tried an ensemble classifier. And now, what we mean by this, is there a better model we could use? So if you've started out with a simple model, could we use a more complex one? And what I mean by this is when someone says simple model, usually what you'll do is the models, the first ones you come across here are relatively simple compared to the ones you'll end up here. And now the reason you start out with a simpler model is because generally these models are faster to train on whatever compute power you have, and an ensemble classifier such as a random forest or ensemble models in general are generally considered more complex because you're training a bunch of little smaller models at once. And so this is where you'll hear the term simple model versus complex model. Linear SVC is often referred to as a simpler model, and then coming up here to like ensemble classifiers, because it harnesses the power of lots of different models, they're referred to as more complex. So that's kind of what we've already tried, right? We started off with a simpler model and then we moved to something more complex with the random forest. And then if we are trying something more complex like an ensemble method, aka using our random forest classifier, is could we improve the current model? Now in this case, if the model we're using performs well straight out of the box, which is what our random forest classifier does, can we improve the hyperparameters of this model to make it even better? Now, a little note here is that patterns in the data you find, that our machine learning finds, is often referred to as data parameters. And the difference between parameters and hyperparameters is a machine learning model seeks to find patterns in data on its own. So a machine learning model will find parameters in data on its own, whereas hyperparameters are settings on a model that you can adjust. So we'll put this here. Parameters equals model finds these patterns in data, and hyperparameters equals settings on a model you can adjust to. Now we'll put this in brackets because this is a bit of a trial and error process to potentially improve its ability to find patterns. Now we've covered a fair bit of ground, right, just in this one cell before we've even seen to code, but this is kind of setting up the framework for what we're going to cover in the next couple of videos. So let's put that there. Oh, this is a little bit confusing here. We might put a little heading here. Hyperparameters versus parameters. Now, how do you find a model's hyperparameters? Well, that's a good question. Let's check it out. We'll go from Scikit-learn.ensemble import random forest classifier. CLF equals, we'll instantiate a random forest classifier here, random forest classifier. Wonderful. Now, once we have a model instantiated, you can find its hyperparameters by calling the function on it, getParams. Wonderful. Now, these are all different hyperparameters that we can adjust on our random forest classifier. And now, if you're looking at these and thinking, wow, this is a lot here, this is very confusing, I'll show you where you can find out more about each one. Well, let's go to Scikit-learn random forest classifier. Wonderful. So if we were to go through this documentation, what we're going to see here is parameters. Now, this can be where it gets confusing because I've used the word hyperparameters, but Scikit-learn kind of defines them as parameters. The reason why it's parameters here is because in Python terms, each of these is a parameter that you can pass this function to adjust. But in reality, these are hyperparameters. So this is where this list comes from. If we were to read through all of these, we could come to the Scikit-learn random forest classifier documentation and read through all of them and find out what exactly they are. Then if we come down here, Scikit-learn will include a few notes about the random forest classifier and little tips on how we can adjust the hyperparameters. Now the same goes for any other model that you might choose. If you click on any of these, you'll come across something similar like this, documentation which will tell you the model's hyperparameters that you can adjust. Okay, now you still might be thinking, I'm still not getting the concept of hyperparameters. And so we come to this little diagram. This may help your understanding. Improving a model via hyperparameter tuning. So if we imagine this food source here as our data, and what we want a machine learning model to do is figure out the patterns that it can use to make our favorite dish. If you're cooking your favorite dish, if this is you cooking here, not a machine learning model, what you might find is that if you put the oven on for 1 hour at 180 degrees, your favorite dish, the roast chicken dish, doesn't come out exactly how you want it. But after a little bit of practice, after a little bit of trial and error, you find that if you cook it 1 hour at 200 degrees, your dish comes out exactly how you want it. Perfect. Now, the analogy here to understand is that in our case, adjusting hyperparameters is like adjusting the temperature on the oven. Our initial machine learning model, straight out of the box, may be this oven here, cooking at 1 hour at 180 degrees, and it may find some patterns in how to combine these ingredients together to get our favorite dish, but it might not be just exactly how we want it. So what we do is we try a few different parameters, a few different hyperparameters, and eventually we figure out we want to change the temperature to 200 degrees, and that brings out our perfect dish just the way we like it. The same thing goes with our machine learning models. If we just used our random forest classifier as it is, as it came out of the box with its default parameters, these ones here, it may find patterns in our data pretty well, which it is. It's doing about 85% accuracy. But what we might be able to do is adjust these, much like our setting on our oven, and so that it finds these patterns in the data a little bit better than what it does straight out of the box. Whew. Now, again, this is a lot to take in, but don't worry. It took me a while to understand this concept as well. So we're going to look at, over the next few videos, 3 ways to adjust hyperparameters. The first one is by hand. So we'll try and tune them by hand. The second one is randomly with random search CV, which is a function in Scikit-learn. And the third one is exhaustively with grid search CV. Okay, so have a little bit of a read over this. Just read through here. If you don't fully grasp it yet, that's completely fine. But just remember, this is what we're going to cover in this section, is we're going to improve a model focused on hyperparameter tuning, and hyperparameters are settings on a model you can adjust to potentially improve its ability to find patterns in data. Much like if you were cooking your favorite dish, you might adjust the temperature of your oven from its baseline setting of 180 degrees to get the perfect outcome of your favorite dish. So keep that in mind, and I'll see you in the next video. So let's start diving into different ways we can improve our models using hyperparameter tuning. The first one here is by hand. So let's make a little heading. 5.1, tuning hyperparameters by hand. And so far, we've talked about dealing with training and test data sets. A model gets trained on the training set, it finds patterns, and then it gets evaluated on the test set, so it uses those patterns. But hyperparameter tuning introduces a third set, a validation set. So if we have a look here, this is what it's going to look like when we tune hyperparameters by hand. So if we were starting with 100 patient records in the case of our heart disease problem, and now again, this may change depending on what problem you're working with, and I've just used the number of 100 because it's an easy number to picture. So this is our starting data. And what we might do is split it. This is what I mean by 3 different sets. So we split. We might use 70 to 80%, so 70 patient records as a training split. We might use 10 to 15% as a validation split. And we might use 10 to 15% on a test split. Now, of course, you can adjust these numbers. These are just some common numbers you'll see used. And so, naturally, the model gets trained on these, is what we've seen before. And usually without the validation set, our model will get evaluated on these. But now because we have a validation set, this is where we're going to tune our model settings, aka the hyperparameters get tuned on the validation split. And then, finally, as normal, a model gets evaluated on the test split. And now the analogy here is, if you remember right back at the start, it's the most important concept in machine learning is the 3 sets. So this was right back in the start, Machine Learning 101. The training set is analogous to, say, you were at a university course and you were learning the course materials. The validation set is where you would test your knowledge a little bit and see what you need to adjust. So you would get the practice exam from your professor and you try it out and you go, oh wow, I'm doing terribly at questions 1, 2, and 4. Maybe I need to adjust the way I approach this. And then you do the practice exam again. And once you'd improved your skills on the practice exam, you'd feel a little bit confident and you'd finally really evaluate yourself on the final exam, which is the test set. So, how would we do this with code? Let's come back to our notebook. Tuning hyperparameters with hand. Let's make 3 sets: training, validation, and test. So, what we'll do is we'll just remind ourselves of our get params. We'll remind ourselves of our random forest classifier's baseline parameters. So these are all the baseline parameters, aka the settings on our model which we can adjust. And now, in fact, which ones are we going to adjust? Well, after reading the random forest documentation, and again, you can do this for any machine learning estimator or model with Scikit-learn, we start to get an idea of how we could adjust each setting. And even with some of the models, there'll be some notes on different hyperparameters Scikit-learn suggests to change. That is kind of like the ones you want to change first to try. And so after reading through that, after going through that, so in our case, we're going to try and adjust the following. So we want max depth. Actually, we'll put these in backticks because we know that they're code. Max depth, max features, min samples leaf. If none of these make sense, remember the definition to all of these is in the documentation for any model. So if we come up here, min samples leaf. The minimum number of samples required to be at a leaf node. And you can read more in depth in what a leaf node is if you check out some resources on a random forest in depth. But for now, we're just focusing on how we can adjust hyperparameters of a machine learning model. Min samples leaf, and min samples split, and n estimators. Wonderful. So these are the hyperparameters we're going to adjust. And now we'll use our same code as before, except this time we need to create a training, validation, and test split. We'll just use these splits here. So the training split will create with 70% of the data. The validation and test sets will each contain 15. And we'll get some baseline results. So we've kind of already got them, but we'll do it again, get some baseline results. And then we'll see how we can tune the model's hyperparameters by hand. And since we're going to be evaluating a few models, I think it's important that we create an evaluation function. So this is what you might want to do, whatever model you're working on, is create functions if you know you want to do something more than once. So it saves out writing lots of code. But again, that's probably a bit different to what we've seen in the past, right? We know we like to write everything out by hand. We'll just leave a little doc string here. Performs evaluation comparison on Y true labels versus Y pred labels. And now, as we saw in the evaluation section, the main thing evaluating machine learning model does is it compares its predictions versus the true labels. So that's what this function is going to do. So because we're working with a classifier, we want accuracy score Y true, Y preds. We also want precision. And now we might actually note here on our classification model, because if we use this evaluate preds on a regression model, we're putting in classification metrics, we're going to get errors because a regression model predicts different things to what a classification model predicts. Precision, and then we want recall, of course, equals recall score. And now again, you could adjust this evaluate preds function for what you need, but I'm just going to include some of the most common metrics that we've covered for the classification models, some of the things you want to pay attention to for basically all of your classification models. Y preds, and then we'll create a dictionary so it can return the predictions so we can compare them with other predictions later. Round accuracy, we'll go to 2 decimal places. Yep. Precision, round, precision, 2. Now always remember, if this seems like a lot, it's because first of all, it kind of is a lot to take in one hit. And the second thing is that I've had a fair bit of practice with this. So I inherently know what to use. Again, I'm always learning, but I've just had a bit of practice building these specific kinds of systems, and these patterns come up time and time again. We go print. We want, just to give us a little bit of printout of what's going on, we'll go accuracy times 100, and then we only want 2 decimal places. That will be enough. Then we'll go the same thing. Go F, precision. This can be precision. We won't need to times that by 100. That can just stay at 2 decimal places. Oh, we need a string ender. Wonderful. Print. Then we're going to go recall. This is a lot to type out to begin with, but because we'll be able to reuse it, it's going to save us down the track. And then finally, we want print F1 score. We're making it. We're finally making it. Excellent effort. There we go. Okay. Oh, and finally we want to return our metric dict. Now what is happening here? Well, essentially this function just takes some true labels and some prediction labels from our classification models. We know this from the string here. It's going to compute different evaluation functions here, and then it's going to return a metric dictionary so we can save that for later. And it'll also print out some metrics so we get a printout as soon as we run this function. So it's just an evaluation function for our classification models. Wonderful. And I'm going to save the notebook here as always. And now how exactly would we create these train, validation, and test splits? Well, our train test split function that we've seen before, remember this one? Train test split. So this one only returns train, splits arrays or matrices into random train and test subsets. So this one only splits into train and test sets. So what we'll need to do is we'll need to manually split our data into train, validation, and test sets. And so to do this, we can, how can we do this? Because our data is in a data frame, heart disease, we should just be able to do it using some good old math and indexing. Let's see how we would. So from Scikit-learn, we'll import our model first, even though we've already instantiated a random forest classifier. Let's go np random seed, and then we'll shuffle the data. Why are we shuffling the data here? If we're splitting into train, validation, and test split, we want to mix it up, make sure it's not just the same. The records are coming in the order that they come in. If we're using slicing to create our train, validation, and test split, we want to make sure all of these records are jumbled up. So that's what we'll do. We can shuffle it using pandas sample function. We'll do frac equals 1 for 100% of the data. This is just going to take the heart disease, sample it, this is randomly, and then reassign the heart disease data frame to its normal variable. So it'll just take this, sample a bunch of rows at random, and then reassign it to this variable, aka shuffling the data. Now the data's been shuffled, we'll split into X and Y. Actually, we might save that to heart disease shuffled. That's a better idea. X equals, this time we need heart disease shuffled. And then we're going to drop the target column here. This video is dragging a little bit on, but this is an important concept, right? We're going to see here, it'll all be worth it because we'll be able to improve our models using hyperparameter tuning. Split the data, validation, and test sets. Wonderful. So the train split, how are we going to do this? Well, we need to create a number that we can use for slicing. So we want 70% of the length of our data. So you see what's happening here. Train split, we need a number. We need 70%, so 0.7 times the length of heart disease shuffled. And this is going to be 70% of data. And then we need a valid split, which is going to be, do you remember? Do you remember what the split is? 15%, that's what we've agreed on. Wonderful, so we can do that in the same way. That will be train split. Because we want to index, we want the next 15%. So train split plus 0.15, the length of our heart disease shuffled data frame. This is 15% of data. Wonderful. And so X train, Y train is going to be the X data up to the train split, and the Y data up to the train split. Wonderful. And then X valid, Y valid, sorry, is going to be the X data from the train split to the valid split. And the same thing for Y is going to be the Y data from the train split to the valid split. And then we're going to have X test is going to be, and Y test is going to be the X data from the valid split onwards. So the rest of the data. And then Y from the valid split onwards. Whew! That was a lot so far. Let's just see what's going on, right? Let's go len, print it out, X train, and then we want len X valid, and then we want len X test. Okay. So the training set has 70% of the data, aka 212 rows. The validation set has 46 rows, 15% of the data. And the test set has 46 rows. So that's 15% of the data. There's different amounts here, even though they're both 15%, because we've used round. We have an odd number of samples in the heart disease shuffled data set. So there's going to be a spillover of 1 somewhere. That is perfectly fine. Okay, now we have our splits. We can do CLF. We'll instantiate a random forest classifier. And now, because we've passed nothing here, this is going to instantiate it with the baseline parameters. So if we do this, clf.getParams. Oh, that's not an attribute, that's a function. So without passing anything to here, our random forest classifier, it instantiates the random forest classifier with the baseline parameters, aka this. And so that's what we want, because we want to make some baseline predictions. So we go clf.fit. We're going to fit it on the training data as usual. And then we're going to make predictions. So ypreds equals clf.predict. No, we're going to predict on the validation data, because we come back here. We want to tune our model on the validation split. So that's what we're basing our metric on. Is we'll first create a baseline metric, which is by running our evaluation function on the validation split. Then we'll adjust the hyperparameters and try our model again on the validation split and see how they compare. So let's go here. So make predictions. We'll call this baseline predictions. And then we'll go evaluate the classifier on validation set. So we'll go baseline metrics, and this is where our evaluation function will come in handy. Metrics equals evaluate preds y valid. So see how we passed it the y, the validation set, and y preds. And then we want to go baseline metrics. Oh, what have we got? Local variable, accuracy, reference before. Oh, this is what we've missed out on. This needs to be accuracy score. Let's run this again. It's done terrible. Now, what is going on here? Accuracy, 0.22. Have we done this correctly? Oh, there we go. That's why. We've used our original. See, that was like that. We need to use heart disease shuffled because otherwise our model was predicting the original labels rather than our shuffled labels. So that's all we missed out on there. There we go. Whew. So we're getting this warning here that the value of n estimators will change from 10 in version 0.20 to 100 in 0.22. So this is our baseline metrics now. What we've done is we've created a train, validation, and test split. We've instantiated a model just as we had done before. We've fit it on the training data here. And then we've evaluated the baseline parameters, baseline hyperparameters on the validation set and got these metrics. So if we were to try and improve our results, if we were to try and adjust a model's hyperparameters, these ones here on our random forest, by hand, because that's what this section is, tuning hyperparameters by hand, how would we do so? Let's take this warning as an example of changing a hyperparameter. Let's change, and again, if you're using Scikit-learn 0.22 or above, you won't get this warning, but since we're getting this warning, we're going to try and adjust our hyperparameters. We'll change n estimators, which is this one here. We'll change it from the baseline of 10 to 100 and see if we get a different score on the validation set. Create a random seed, 42. What we're going to do is create a second classifier with different hyperparameters. Because remember, instantiating our random forest classifier up here, passing it nothing, instantiates the classifier with the baseline hyperparameters it comes with right out of the box. So like using your oven's predefined settings when it comes out of the box to cook your favorite dish. These scores aren't really helping us out here. We want a better model. We'll create CLF2 and we're going to adjust the hyperparameters like you would adjust your oven to try and improve that favorite delicious roast chicken dish that you're making. Maybe you're preparing for a big function that all your friends are coming over and you've promised them a great dish, so you're trying to perfect it. That's what we're doing with our machine learning model. So again, same thing. Same data, fitted on the training data, but this time we've got CLF2, which is using n estimators as 100 rather than 10. And now, again, we could try different settings for all of these features here, the ones that we're going to try and adjust. But we might start with just one, see an example of it. And then we'll go make predictions. So ypreds2, because we're using CLF2, CLF2.predict, xvalid. We're doing the same thing as up here. The baseline predictions are on the validation set. And now make predictions with different hyperparameters on the same data. So different model, same data. And now we're going to evaluate the second classifier. CLF2 metrics equals, we're using our evaluation function again already, the one we created before. And we're saving a fair few lines of code by just calling it like that. All right. Now let's check it out. Okay. So now if we compare, using the baseline hyperparameters that our model came with, what can we see that's different here? All we've changed is n estimators equals 100. So we've adjusted one dial on our model. So like adjusting one dial on your oven. We can see a slight boost in accuracy on the same data. So CLF2 has a slightly higher accuracy. It's got a higher precision, but a lower recall, and at the same F1 score. Okay. That's giving us a little inkling that maybe if we kept going with different hyperparameters, we kept trying to adjust them by hand, we would eventually just hopefully keep improving these metrics. So what would you think we would do next? If we go up here, maybe we try to change the max depth. So what's the default max depth? We find it in here. Max depth is none. So maybe we'd look at the documentation and go to the different variables that max length can take. So it can take integers or none. Default is none. The maximum depth of the tree. And doing our research, reading the documentation, we see some different values for max depth. So then we'd go back to our model here, and maybe we create CLF3 equals random forest classifier. This time we'll keep n estimators as the same, equals 100. And then we'll change max depth from none to equal 10. Now, I haven't made this number up. I've done some research, read the documentation, and figured out different ideas for max depth. And then we might do the same thing as what we've done here, evaluate our third classifier. As you might have guessed, or as you might have thought, if we're going through and adjusting all of these by hand, adjusting all the knobs by hand, that's going to take a fair bit of work, right? So just like perfecting your dish in real life, like if you're making a favorite chicken dish, everyone's coming over for dinner, you're trying to adjust the settings on your oven, you may have to go through a bit of trial and error, right? You might cook it once and then it's not that good, and then by the 10th time you're starting to get really good. But that could take a lot longer with what we're trying to do here, writing code. If we have all these different settings up here, trying to change these, trying to find the best settings, that could take far longer than what we have. And the rule is, in code, don't repeat yourself. So you might have guessed, Scikit-learn has a way, a method inbuilt that can do this for us. Try a bunch of different settings for us. And that's randomized search CV. But we're going to have a look at that in the next video. This one's already getting far too long. But the main takeaway here is that when we're tuning a model's hyperparameters, you can think of the training set as like the course materials where you're learning the foundation data. That's the training set. And then on the practice exam, you're refining what you know. So you've already learned all the baseline patterns like our model. And then with the validation set, we're adjusting the settings. So we're refining what the model knows, how it learns different things before we test ourselves on the final exam. So in AKA, before we evaluate our model on the test set. Now don't worry if you're feeling a little bit overwhelmed, go back through the code that we've written, check it out. You could try out adjusting a few different hyperparameters yourself, but if not to worry. We're going to see in the next video how we can use a module in Scikit-learn to try different hyperparameters for us. Welcome back. And in the last video, we checked out how to tune a model's hyperparameters by hand. And we figured out by the end of it, once we'd written some code, once we've split our data into train, validation, and test sets manually, we created an evaluation function. Yeah, and at the end, we figured out, tuning a model by hand, that sounds like a lot of work. And you're right, it would be if we went through and tried a whole bunch of different hyperparameters. But luckily, the developers of Scikit-learn have also come across this problem and have created randomized search CV, which stands for randomized search cross-validation. Let's see how we'll tune hyperparameters, so aka adjust the settings on our models to make better predictions, or hopefully make better predictions, using randomized search CV. So let's go here and create another heading. This can be 5.2. So hyperparameter tuning with randomized search CV. Beautiful. First thing we'll do is we'll import it. So from sklearn.model_selection, import randomized name. We might be able to press tab here. Randomized search CV. Beautiful. Let's see an example of how we use it before we check out the doc string. So what we'll do is we'll create a grid of hyperparameters. And by grid, I mean dictionary. And I've typed grod here. A dictionary of hyperparameters we'd like to adjust. So if we come back up here, these are the hyperparameters we're going to adjust. So what we're going to do is create a dictionary with the hyperparameters we'd like to adjust as the keys, and then the values we'd like to try as the values of the dictionary. So let's do that. So n estimators, that's a key. We're going to pass it a list. So 100, 200, 500, 1000, and 1200. Beautiful. Now, if you're wondering, Daniel, where are you getting these values? Well, remember, as always, with any model or estimator in Scikit-learn, there's extensive documentation on it, which tells you some of the settings that you can change on the model So what I've done is I've read through here, read through the examples, done some research, and found different values for the hyperparameters we can try. So go here, none, 5, 10. So if it looks like I'm just throwing out values here, trust me, they're not just sort of thrown out values. They are based upon some research and some experience. And don't worry, you won't begin with that. No one begins with that. It takes a little bit of practice to go through it. That's why we're having a look hands-on at all these different functions that we can use to improve our models. Wonderful. And then we'll do 2 more, which is min samples split. 2, 4, 6, comma here. Min samples leaf. And let's see how we'd implement randomized search CV. So we'll set up a random seed. We'll split into X and Y. So we want heart disease, shuffled actually, because that's what we've used before. Dot drop, oh actually we need to make X here. Dot drop, target, axis equals 1, and we'll make Y here. So heart disease, shuffled, target. Beautiful. And we're going to go split into train and test sets. Huh? You might be wondering, why are we only using train and test here? We've just created a validation set. Now, we'll get to that. Y train, Y test, train test split, X, Y, and we'll use a normal split here. So test size equals 0.2. Wonderful. And then we're going to instantiate random forest classifier. CLF equals random forest classifier. And jobs equals, now we could do -1 here, but at the moment -1 is broken for me. Now that'll make sense in a second, but njobs stands for how much of your computer processor are you going to dedicate towards this machine learning model. And -1 means all of it. So by default, njobs is 1. Or actually, what is the default njobs? Let's go here. njobs equals none. Okay, so we'll set it as none. Actually, I'll just set it as 1. So different values you pass to njobs will dictate how much of your computer processor that you want to dedicate towards a machine learning model. And now, once we've got a classifier instantiated, we'll set up randomized search CV. So we're going to pass it. We're going to call it RSCLF. So what that's going to do is it's just appending RS to it for randomized search. And now, randomized search CV, the first parameter it takes is estimator equals CLF. So we're passing it this random forest classifier we've instantiated. Param distribution is the next one. We're going to pass it our grid. So this is grid up here. And the next thing is we're going to define an iter. So equals 10. And this is the number of models to try. We'll do 5-fold cross-validation. And then we'll set verbosity verbose equals 2. Whoa. This is some code we haven't seen before. So what is happening when we run randomized search CV? We look at the docstring, press Shift Tab in here. Oh, it's because we haven't imported. That's all right. We'll press Shift Tab here now. So what's the docstring here? Randomized search on hyperparameters. Randomized search CV implements a fit and a score method. It also implements predict prober, decision function, transform and inverse transform if they implemented in the estimator used. So randomized search on hyperparameters. That can sound a little bit confusing. What does it mean by randomized search? So That's in the name, randomized search CV. CV is for cross-validation, which is where you might recognize this parameter, CV equals 5. So that means we're using 5-fold cross-validation. So 5-fold cross-validation. This is why we don't necessarily have to create a validation set here. So what randomized search CV will do is it'll take our classifier and it'll take a param distributions grid, which is this, and it's going to search over this grid for 10 different times, different combinations of these parameters at random. So for example, on its first iteration, so because it's doing n iter equals 10, it's going to do this 10 times. On its first iteration, it might try a model with 10 estimators, a max depth of none, max features set to auto, min samples split set to 2, min samples leaf set to 1. And then on the next iteration, so iteration 2 out of 10, it might try 1,000 estimators, 30 as the max depth, auto as the max features, 4 is the min samples split, and then 4 is the min samples leaf. Then it's going to keep going that up to 10. Now we could set this to 100, to 1,000. I don't think there's even 1,000 combinations in here. If you went through, you could go 6 times 5, that's 30, times 2, that's 60, times 3, that's 180, times 3, that's 460 odd. And the math may be a little bit off there, but you get the point, right? If you went through all of these and tried to combine them in every single combination, that's going to be a lot of different models. So let's see this in action. So once we've set it up, instantiated randomized search CV, we'll go here, fit the randomized search CV version of CLF on rs clf.fit xtrain.ytrain. Now the reason we only have to fit it xtrain and ytrain is because the CV in randomized search CV stands for cross-validation. So that is what it's going to do. It's going to automatically make our validation sets for us, which is a beautiful thing. So if we come back to our diagram, it's going to take our data, and then it's going to try different hyperparameters cross-validated on different hyperparameter settings. So that's what it's going to return. It's going to figure out which combination of these hyperparameters is the best, up to 10 different models. And again, we can increase this if we wanted to try more combinations. So let's see it in action. So this is where we've set the verbose to 2. It's going to output and tell us what's going on. So fitting 5 folds for each of 10 candidates, totaling 50 fits, aka it's trying 10 iterations of different combinations of parameters in this grid and splitting each combination 5 times because CV equals 5, totaling 50 fits on the data. So it's going to run this fit function 50 different times using different hyperparameters on different splits of the data. So we can see here, the first split it's trying is n estimators equals 1200, because this is one of our hyperparameters up here. And remember, each split, each iteration, it's going to pick combinations of these at random. It's also set min samples split to 6 here, min samples leaf to 2, max features to square root, and max depth to 5. Okay, and then if we were to scroll through here, we can see all of the different combinations it's tried. So let's pick one at random, this one here. So this combination is trying n estimators equals 200, min samples split equals 6, min samples leaf equals 2, max features equals square root, and max depth equals none. And then it's going to keep going until it's finished. It's going to give us a warning here. So let's see. Once it's finished, what we'll be able to do is call best params on it. So if we go rs clf.best params, and this is going to show us the combination of hyperparameters, which combination of these got the best results. Wonderful. So where n estimators equals 200, min samples split equals 6, min samples leaf equals 2, max features equals square root, and max depth equals none, they were the best cross-validated results across 10 different models. And now, when we call predict on our randomized search classifier, by default, it's going to use these parameters. So instead of finding these by hand, randomized search CV has found them for us. So let's do it. Let's make predictions with the best hyperparameters. So what we might do, RSYPreds equals RSCLF.predict. And we could use the validation set here, but in our case, we're going to use the test set. And then we'll go evaluate the predictions. RS metrics equals evaluate Y test RSY preds. Oh, our function is supposed to be evaluate preds. There we go. Wonderful. So if we come back up here, did we see an improvement here? No, we didn't. And so this is the sort of where the experimentation comes in hyperparameter tuning. You won't always find an improvement after running something like this. Maybe we could run it for longer and try 50 different combinations. And after it's tried 50 different combinations, it will find some parameters which end up being better than our manually tuned result. But what I hope you're starting to see is that using randomized search CV, rather than running through all these different settings by hand, it gives us a way to codify or functionize the tuning of hyperparameters. And so now there's one more way we can use to improve our model's hyperparameters, and it's with grid search CV. So it's kind of similar to randomized search, but it's got one key difference. We'll have a look at that in the next video. Welcome back. In the last video, we saw how to tune a model's hyperparameters using randomized search CV. And what that did was we defined a space or a dictionary of different hyperparameter values we'd like to try, and then randomized search CV combined these parameters at random and built a classifier with different settings, different hyperparameters, and then evaluated them all using cross-validation. Or we might change this back to 10. We don't want 50 models running off. And then after trying 10 different combinations, it found the best parameters to be this set of values here. Then after evaluating them, we saw it didn't really do as well as our previous model up here where we tuned just by hand. And so finally, a workflow you might end up with when you're tuning hyperparameters is starting off by hand and then using randomized search CV across a space of hyperparameters. And then once you've found some pretty good hyperparameters, you'll probably finish up with grid search CV. Let's see that in action here. So 5.3, hyperparameter tuning with grid search CV. Beautiful. And let's check out our grid. So our grid at the moment is, you might notice the grid search CV has the word grid in it. And our grid of hyperparameters at the moment are these values here. And the key difference here between randomized search and grid search CV is that randomized search CV has a parameter called niter, which is what we saw up here, which we can set to limit the number of models to try. So in our case, we used 10. So if we look back up here at the top of this code, fitting 5 folds for each of 10 candidates, totaling 50 fits. The key difference between randomized search CV and grid search CV is that grid search CV is kind of like a brute force search. It means it will go through every single combination that is available here. So if we have a look, we've got 6 values there. So it'll be 6 times 5 times 2 times 3 times 3. So there's 6 parameters here, there's 5 here, 2 here, 3, 3. In total, 540 different parameters that it would try, or combinations of parameters. Now that's a lot. And then cross-validated, so times that by 5. So 2,700 models. That's a lot, right? That's going to take a lot of compute power. Training one model might take long enough time, but training 2,700 of them, especially if you're working with a large data set, probably not going to be suitable for your laptop. You may need a big computer. Or we can reduce the search space. So let's see that in action. So what I mean by that is we'll create grid 2 using a little bit more of a confined hyperparameter space. So in essence, just reducing the number of hyperparameters grid search CV has to go through. So let's see this in action. What we might do is just copy this. And now how would you create grid 2 in practice? We could just copy and paste it, which we've done. I want to line these up so it all looks Pythonic. There we go. Now we could just copy and paste it and then just delete these at random. Delete, delete. But we might not do that. Say we've gone through randomized search CV and it's gone through, let's say we up this to 50 different models like we had before, but in our case we've only actually done 10. We might take these parameters, the best params from our randomized search CV, and use them to influence where we'd like grid search CV to run. So let's do that. Our best parameters is 200, 6, 2, square root. So what we might do, remove 10, keep 500 there, remove these two. Yep. Max depth is none. So we might just keep that as none. So it's only got one option there. And then for square root, we might actually keep that as auto or square root. And then what else do we have? Min sample split is 6. We might get rid of 4 and 2. And then what we might do, min samples leaf. So we might keep that as 1 and 2. So what have we done here? Well, what we've done is we've reduced our search space of hyperparameters. So now, if you remember, we had 540 different combinations there. What do we have? So we have 3 times 1 times 2 times 1 times 2. So 12, and then it's going to be cross-validated 5 times, so we can adjust this using the CV parameter. So 60 versus 2,700. So that's a lot less parameters there. So how would we do this in practice? How would we use grid search CV to find the best hyperparameters in this space? Well, as always, let's see it in action. From Scikit-learn.modelSelection, import grid search CV, and we want to import as well train test split. We probably already have that. We can put that there. Random seed, wonderful. Split edit. What we might do actually is just bring this code up here because it's the exact same code that we want to use before. So we'll just take this, except we're going to change one thing. Come down. Wonderful. So we're using the same data set as our randomized search CV, making the same split. We're instantiating a random forest classifier, but this time we're going to set up grid search CV. Grid search CV. Wonderful. Grid search CV. And then we're going to fit it, the grid search CV here. And now there's a different parameter here. So this one is going to be param grid, I believe. It's not going to have an iter because grid search CV is like brute force. It tries every single combination. And we want it to try our grid 2, not grid 1, because it's got a few less options there in grid 2, as we saw before. So we'll come down here, keep cross-validation as 5-fold. Verbose equals that. Okay, now let's step through what's happening. So we're importing grid search CV. We've created grid 2, which is a refined search space of different hyperparameters, so different settings. So much like if you were working on your favorite meal, adjusting your oven, if you set the temperature to 400 degrees, that's way too high. So if it starts off at 180 degrees and it does okay, you might go, why would I go right to 500 or 400 degrees when I can just make a little jump to 400? So that's why we've created grid 2. We've based it off the best parameters or the best hyperparameters that our randomized searched CV or the randomized search CV has found. So let's do it. Let's build a random forest classifier using grid search CV. So here's how it's going to go again. Same thing again, fitting 5 folds for each of 12 candidates, totaling 60 fits. Now what grid search CV is going to do, just like randomized search CV, It's going to go through all of these different hyperparameters and pass them to our random forest classifier, trying each different combination, and then eventually, when it's finished, we'll be able to go GS CLF best params. Wonderful. So it might take a little while with grid search CV. This is something to keep in mind. The more hyperparameters you have in here, the longer it will take grid search CV to run because it has to try every single combination of hyperparameters in here. So now, as we did before, we can evaluate our grid search classifier by making predictions with it and then using our evaluation function to figure out how it did. So let's do that. GS CLF, we'll go GS Y preds equals GS CLF dot predict. We'll predict on the test data as well, X test, and then we'll go evaluate the predictions. GS metrics equals evaluate preds, our function one that we defined a couple of videos ago, and then we'll go GS Y preds. Wonderful. And now again we see a slight decline in accuracy. And that just goes to show how much of a process tuning hyperparameters can be, right? It's all about that trial and error. What you could do to fix this is go back up. Your workflow would probably be try a few settings by hand, as we did right back up here. Tuning hyperparameters by hand. This is the workflow you'd probably do. Try adjust a few of these by hand, see if you can figure something out with a validation set like we've done. And then try some hyperparameter tuning using randomized search CV. You might, in this case, up this number to 20 or 50 or so, or whatever arbitrary number that you find. Again, this is all experimentational to try and figure out what hyperparameters are better. And you might even change the grid that you're searching over based on the hyperparameters you find in the Scikit-learn model documentation for the model that you're using. And then once you've found some good hyperparameters using randomized search CV, you might take those hyperparameters, these ones here, best params, and then create another grid to grid search over, like we've done here. In our case, it hasn't improved our model's metrics, but this is where we'd probably start to experiment a little bit more, try a few different other metrics, try a few different other hyperparameters. But for completeness, what you'd probably do then, after you've tried a fair few different hyperparameters, you've created a baseline model with the default settings, you've tried to adjust them by hand, you've tried to adjust them by randomized search CV, and you've tried to adjust them by grid search, you're going to want to compare your models. So let's compare our different models' metrics. Wonderful. And to do so, we're going to create a data frame. So PD, this is why we've been returning dictionaries from all of our models and our evaluate preds function. So baseline is going to be baseline metrics, and then CLF2 is going to be CLF2 metrics. Type in M's here when we don't need them. Random search is going to be RS metrics, and then grid search is going to be GS metrics. Wonderful. And then to see it in action, we're going to go compare metrics, which is just our data frame that we've instantiated here. Oh, we might need to move this up there. There's going to be an error there in there. That's an extra squiggly bracket that we didn't need. Dot plot, dot bar, fig size equals 10, 8. Let's see it. Wonderful. So this is going to compare all of our different classification models' metrics in the one space. So we can see our baseline model is the blue. So on this one, it didn't get the best here. It was more of a tie between CLF2 and random search. On precision, CLF2 is out in front. On recall, baseline is out in front. And on F1, it's a tie between baseline and CLF2. And again, you could adjust this graph to make it more visible. This is just to demonstrate different metrics. And so this is the kind of communication you do for not only yourself, but for your teammates, or if you're reporting to someone in a project, is to show them the different models that you've tried and then how they perform differently on different classification metrics. If you're working on a classification problem, of course, you can do the same sort of process with a regression problem. And now, depending on what you need for the project will depend on which model. So say you wanted a model that optimized recall. In this case, you might use the baseline model. Or if you wanted a model that optimized precision, you might choose the CLF2 model. And if none of these metrics really worked for you, you might continue to try to find some better ones through random search or grid search. And now, we finally got to the end of how you can improve a model via hyperparameter tuning. And again, there's a lot to take in here. The key point is to remember it's an experimental process. Improving a model through hyperparameter tuning there's no sort of written law on how you do it. But the point is to just keep trying, see if you can figure out something, see if you can get yourself familiarized with different hyperparameters that different models have, such as the random forest classifier, and just remind yourself that the first model that you make is more than likely not the best model that you'll have. It's a baseline model and it can be improved upon. And so, built a model, we've tried to improve it. Let's say you've decided you're going to focus on recall or something like that. You may want to export your model so you can share it or use it in some sort of deployment setup. So in the next section we're going to look at, if we look at our list here, what we're covering, we're going to look at how to save and share and load a model. So save and load a trained model. The benefit of this is that you won't have to retrain a model like we've done in the past few sections. So go back through, check out what we've covered with hyperparameter tuning, how to improve a model, hyperparameter with grid search CV, try it out with randomized search, try it out by hand, and I'll see you in the next video.
Hey there, it's Andre again with your quick tip. That is, let's talk about correlation analysis. What does that mean? Well, correlation analysis simply means which attributes have correlations. So let's say one column is correlated to another column. Let's say we're trying to sell our home and there's two columns. One column is the size of the land that the house is on, and the other column is the size of the house and the floor space. Now, let's say that when we're analyzing our data, we notice that pretty much all houses that have a large land size also have a large floor space size, and they're just correlated. The prices go up the same every time the land increases and every time the floor space increases. In this case, these attributes have high correlation with each other. In this case, we can actually remove this from our analysis or from building our model because it might not affect our model. This gets to our next point of forward-backwards attribute selection. What does this mean? Well, we can try training our model using different techniques. Backward attribute selection essentially says train the model on all the attributes and then slowly start taking away attributes or columns to train your model. Does that affect your model? Does it improve the model? Forward attribute selection is the opposite. Start with just one column when you train the model and keep adding one attribute at a time until you get the accuracy to plateau. That is, if you keep increasing columns and let's say after the 50th column, all the other attributes that you add just don't improve the model, well, then maybe we might not need it. This idea of correlation analysis, the forward-backward attribute selection, are all ways for us to test our model, reduce our data if we want to, and play with our model instead of just assuming if we include everything will make the model better. That's often not usually the case. All right, back to Daniel.
Okay, everyone. I hope you're as excited as I am. Why? Well, because we're on the home stretch. We're up to number 6, save and load a trained model. So we've gone through all these steps here. We've seen how to improve our models with hyperparameter tuning. And let's say we're at a point where we've improved our model to the point that we're happy to either share that with one of our colleagues or something like that, or export it and save it and put it in one of our applications so that our customers might want to use it, might want to access its predictions, something along those lines. Essentially, we want to take our model that we've trained, we've got these results, export it to file, and so that we can import it and use it somewhere else rather than it just being within our Jupyter notebook. So let's create a heading, 6. We'll go saving and loading trained machine learning models. Beautiful. And there's 2 ways we can do this. So 2 ways to save and load machine learning models. First one we're going to cover is with Python's pickle module. And the second one is with the joblib module. So let's check out how we might do it with pickle. So the first thing is to import pickle. And if you're wondering what pickle is, you can go Python pickle. As always, if we're not sure what something is, we can search it up. So Python object serialization. So if you read this, the pickle module implements binary protocols for serializing and deserializing a Python object structure. Well, in our case, if you're wondering what a Python object structure is, in our case, a Python object is our model. So if we want to say, for example, save GS classifier, so say we're most happy with our grid search parameters model, so the random forest classifier we've trained with grid search. If we wanted to export that, this is our Python object. And that's what pickle can help us do. So let's do that. Let's see an example of how we might export our GSCLF, which is a Python object, to a pickle file. So save an existing model to file. Yes, please. And to do so, we're going to use pickle.dump. We're going to pass it the object we would like to save, in our case, GSCLF, our grid searched classifier. And then you can name it something here. So we need to use the open function, so Python's open function for dealing with input and output of files. And in our case, we're just going to go GS random forest model 1. Now you can get as creative as you like with these names. There might be some nomenclature that you decide upon with your team or something like that. That's what you use for your models. But in our case, I've just gone something nice and simple. And .pkl stands for pickle file. And we also pass, because we're writing a file, we pass the parameter WB for write binary. So if we hit Shift and Enter, beautiful, this is going to save our grid search model with this file name to our current working directory. So if we go up here, if we go GS random, oh, we've got 2 randoms in there. So GS random forest. So this is a random forest, really random. 1.pkl. And you can see there's some other model files here. So .pkl, this is one I tried just before. And this is another one we created right at the start where we were looking at a Scikit-learn workflow. And now, if you've exported a fair few of these models, you might want to put them in like a model file, like we've got our data in a data file. So this is just one way to tidy up the directory. But you can see the one we've just saved here. That's seconds ago. Now, if we come back, how would we load that in? Well, we can do it with pickle as well. So load a saved model. So we're going to go loaded pickle model equals pickle.load. Now, the advantage here is that because we've saved a model to a pickle file, and because it's stored in our directory here, is that someone who wanted to use our model won't have to go through all of the training steps that we've done above. They can just access the model and be able to make predictions by loading it in. We could copy this file name here, but we're just going to type it in GS tab. We use tab autocomplete for that. And now because we're reading in a file, we pass in the parameter RB for read binary. Wonderful. So that's loaded in our saved model. Now the way to check it is we can make some predictions. So to see if this model, if it actually worked, if we saved it and we can use it to make predictions, well then we're in a good place. We want to do loaded pickle model.predict. Now, similar to how we made predictions before with our GSCLF, we're just going to run this exact same line here, but make predictions with our pickled model. Predict on the test data set. Wonderful. And then we'll call our evaluate preds function and compare it, the test labels, to the pickle y preds. What have we got here? Found input variables with inconsistent number of samples. I know what we've done. We've got a data mismatch here. What we'd have to do is, I believe, if we just comment out this line and recreate, we have to reinstantiate our train and test split. That's what we have to do. So maybe I'll just comment out these lines for the time being and run this cell. Come back down here. We load it in. So the mistake here, I believe, and maybe wrong, hit Shift Enter. There we go. Is that our X test had been instantiated somewhere above, and we had to reinstantiate it so that it was reset back to the correct shape. And now the way we can know that this has gone through correctly is if we compare. So if we compare our original GS-CLF predictions, so these values here, if we copy these are the original grid searched classifier metrics. So let's have a look. So this is our loaded models metrics. Accuracy 78.69, same. Precision 0.74, same. Recall 0.82, same. And F1 score 0.78, so the same. That means that our import, our saving our model and re-importing it, so loading it in, has worked correctly. And now again, these names here, you can change them to whatever you like. Same with the loaded variable names. But this is just a quick example of how you can use Pickle to quickly save one of your models to file and then load it back in at a later date if need be, and then make predictions using the exact same loaded model that get the exact same results as the model we originally saved. In the next video, we'll see how we can do the same thing, except this time using job_lib. In the last video, we saw how we can save our existing trained model to a file and then load it back in and then make some predictions that get the exact same results as the original model that we saved to file. We used Pickle to do that. In this video, we're going to see how we can do the same thing with the job_lib module. And again, if you don't know something, you can always go, what is job_lib? Job_lib. Running Python functions as pipeline jobs, and you could go through the documentation here to see how you do it. But let's just see an example of how we do the exact same thing here with the job_lib module. So create a heading, go job_lib. Change that to Markdown, hit Shift and Enter. So the first thing we're going to do, we can go from job_lib, import, dump, and load. You might be able to guess what these two functions do. So to save model to file, we'll go dump GS-CLF, because we're going to save the exact same model that we did with Pickle. So our grid search classifier. We're going to pass it file name. And we'll go gs random forest model1.job_lib. So that's the difference here. We can pass it a file name. Oh, we have to push equals. With Pickle, we use .pkl, which is short for Pickle, of course. But with job_lib, we do .job_lib. And so now if we hit Shift and Enter there, it's going to give us a little output here. Now if we go back to our working directory, we'll see the same thing. So seconds ago, we have gs random forest model1.job_lib. And again, you can change this file name to whatever you want. See, now we've got about half a dozen models just sitting in our working directory. At this point, we might move them into a models file. So we come back here. Now, if we wanted to load in our job_lib model, you can probably guess which function we use to do that. If not, we're going to go through it. So we'll go import a saved job_lib model, and we're just going to import the exact same model that we saved. So loaded job_lib model equals load file name. We just have to pass it the exact same file name as what we saved it as. So gs random, we should be able to hit tab autocomplete, .job_lib, wonderful. So that's going to load it in. Oh, what have we got here? Oh, we missed an inverted comma. File name. We're making typos left, right, and center, even using tab autocomplete. Beautiful. And again, once imported, we can make predictions with our loaded model. So let's see it again. Make and evaluate job_lib predictions. Job_lib y preds equals loaded joblib model.predict x test. Wonderful. And then once again, we'll use our evaluate pred. See how this has come in handy? We defined this function a few videos ago, but now we've used it at least half a dozen times, and so preventing us from having to type out a bunch of different code, the same code over and over again. So joblib y preds, shift and enter, we should get loaded joblib model is not defined. Where are we making this? So loaded job model. We might change that to joblib, and then this should work. Wonderful. So if we compare this is with joblib, these are with pickle. 78.69 tick, 0.74 tick, 0.82 tick, 0.78 tick. So it's again the exact same thing with joblib as pickle. And now, which one should you use? Well, according to Scikit-learn's documentation, let's have a look. Scikit-learn exporting a model. Exporting a model persistence. That's the word I was looking for. So again, if you're thinking of something that you're trying to do with a library, right, just search the name of the library. This is exactly what I do. I typed in Scikit-learn saving a model. That's what I wanted to do. I'll come up to the documentation. After training a Scikit-learn model, it is desirable to have a way to persist the model for future use without having to retrain. That's the main benefit of saving a model, right? So here's an example. So you can use Python's built-in persistence model, pickle. That's what we've seen. And now you could also use, in the specific case of Scikit-learn, it may be better to use joblib's replacement of pickle, dump and load, which is more efficient on objects that carry large NumPy arrays, internally, as is often the case for fitted Scikit-learn estimators. And that's what we're saving in our case, right? We're saving a fitted Scikit-learn estimator, aka GSCLF, which is our fitted grid search random forest classifier. But can only pickle to the disk and not to a string. So what this is saying is essentially, sometimes if your model is large, it might be more efficient because a model is made up of large NumPy arrays, aka patterns in numbers. That's what these NumPy arrays are internally full of. That's what our classifier is probably full of, just different NumPy arrays with patterns between them. That's what it's learned from the data. So what this is saying is that if your model is large, in our case, our models are relatively small because we're only working with 300 or so samples. But if it is large, it may be more efficient to use joblib over pickle. That's the main thing to worry about there. Alrighty. So that's the crux of saving and loading a trained model. Again, we've got them stored in our directory here. If we needed to share this model, that's something we could pass on to our production application or to our colleagues so they could replicate our work or something like that. Now, we're really on the home stretch. Next, we're going to, let's check back at our list. We're going to check out how we can put it all together. I won't spoil anything before the next video. So have a quick break, try to save one of the models that we've trained using joblib or pickle, and I'll see you in the next video. Okay, you've made it. Look how far we've come. We've covered an absolutely massive chunk of the Scikit-learn library, and we're still going to finish it off. We're up to the last section, putting it all together. We've been through an end-to-end workflow. We've seen how to get the data ready. We've seen how to choose the right machine learning model for our problems. We've fitted it to the data. We've used it to make predictions. We've evaluated a trained model. We've improved a trained model. We've saved and loaded a trained model. Now, let's combine all of this. All of this. Could we do it? Could we do it? Now, let's make a little heading. 7.0. Putting it all together. First thing, give yourself a little pat on the back, right? Because we've covered a lot, and so far it seems to be all over the place, and which it is, but not to worry. This is how machine learning projects often start out. There's a whole bunch of different experiments and code all over the place, and then once you've found something which works, the refinement process begins. And now, what would this refinement process look like? Well, let's use, remember our good old car sales regression problem, aka predicting the sale prices of cars? We'll use that as an example. And to tidy things up, we're going to be using Scikit-learn's, let's have a look, Scikit-learn pipeline. To tidy things up, we're going to be using the pipeline class. Now, You can imagine pipeline as being a way to string together a number of different scikit-learn processes in one hit. So similar to like writing a function, right? You're getting a couple of different steps and you're putting them together. Pipeline of transformers with a final estimator. So a transformer or a transform is aka transforming data, getting data ready, and then a final estimator. Estimator, remember in scikit-learn terms, is a machine learning model. So as a refresh, this is our car sales data. There's 1,000 rows, and there's some missing data here, right? So there's missing here, and what we're trying to do is use make, color, odometer, doors to predict the sale price of cars. Now again, this data is imperfect because could you do this? Could you figure this out given enough time? You'd probably realistically need a few more parameters, a few more details about the cars before you could figure out how much they'd sell for. So let's stop talking about it. Let's get hands-on with the code. To start off, we'll re-import the data. So go pd.read csv ... We've saved it in our data folder. Car sales extended. Oh no, our data folder is not up the chain. Oh well. Car sales there we go. Car sales extended data missing. That's what we want. And then we'll have a look. We'll have a quick peek at it. Wonderful. So this is just re-importing this CSV file that we have here. Come back. Now, what did we say? We said we want to use these columns, so these 4 columns, to predict the price column. We'll have a look at our data types. So we've got make, which is an object, that's a string there. Color, which is an object, that's a string there. Odometer, doors, and price, which are... We've kind of talked about doors being a category as well. So odometer is our numerical column. And do you remember what we have to do for our data? We have to make sure that it's all in numerical format before we can build a machine learning model on it. And there's another little roadblock that we have as well before we can build a machine learning model, and that's if we go is NA, so is null.sum, we've got null values in some of our, well, all of our columns. We've got 50 missing data points in each of our columns. So that's also a big no-no with machine learning models. We need to make sure that the data is numerical and that there's no missing values. If we refer back to our keynote, all data should be numerical. This is things to remember, right? And there should be no missing values. Okay? Let's check it out. So what we'll have to do is, if we want to put this all together, we've done this before. We've seen filling data, we've seen converting it, but this time we want to use a pipeline to do so. So the Scikit-learn's pipeline's main input is steps, which is a list that contains a tuple, which has step name and action to take. We're going to see this in a second, but we're just talking through it. And in our case, our steps are, what are our steps? Well, first we need to fill the missing data, and then convert the data to numbers, and then build a machine learning model on it. So let's do it. We'll go here. I want to do this one so it's all in one cell. Let's put our steps here of what we have to do. Steps we want to do. All in one cell. Can we do it all in one cell? Because before, to do this, it took a fair bit of work. But let's see, this is what we're doing. This is our refinement process using pipeline. So step 1 is fill missing data. And then step 2 is convert data to numbers. Wonderful. And then step 3 is build a model on the data. All right, cracks knuckles, gets fingers ready. Let's do them. And if it seems like I'm going through this pretty fast, let me tell you, there's nothing here that we haven't covered except for the pipeline. But what we've learned in the previous videos, you'll be able to deduce, as well as reading the documentation here, what exactly is going on. So import pandas as PD, because we want to do this all in one cell. And then from sklearn.compose, remember the column transformer? And then from sklearn, this is where we're going to import the pipeline class that we're going to take advantage of here. Import pipeline. And then from sklearn.impute, we're going to import simple imputer. This is what we're going to use to impute our data, so fill the missing data. And then from sklearn.preprocessing, import one hot encoder. This is what we're going to do to convert our data to numbers, or sorry, we're going to use to convert our data to number. So getting data ready. These are the imports we're going to use for that. Then the next one is modeling. So from Scikit-learn.ensemble, import our trusty random forest regressor because we wanted to predict a number. And then from Scikit-learn.model selection, import. Have we got that right? Yep, that looks right. I've been known to be prone to typos. Train test split, and we want grid search CV because we've seen grid search being used before, which is going to search for some optimal hyperparameters for our random forest regressor. Okay, now we're going to set up random seed. So we'll import numpy as np. We'll go np random seed 42. Wonderful. Now, for completeness, for doing it all in one cell, we're going to re-import the data. So import data, and we're going to drop the rows with missing labels. So data equals pd.csv. We're going to go to our data folder. This needs to be a string. I'm going to go car sales. Extended missing data, that's the one we're after, the 1,000 rows version. And then to drop the rows that have missing labels, we'll go data.dropNA subset. We'll set that equal to the price column because that's what we want to predict. And that's our label. And we're going to go in place equals true. Okay. So all we've done is we've just replicated this here. And now we've dropped the rows which contain missing price values. So AKA missing labels. Now, what we're going to do here is we're going to start to define the different features of the data set and the different transformer pipelines that we want to take place on that data. So if we come back up here, what transformations do we need to make? We need to change our make and color into numbers. We need to fill the missing values of all the columns in here. And we need to change our doors because it's also a category. We need to change it to a categorical value. So we're going to, actually no, forget what I said about doors. Let's see what we're actually doing in the code. So define different features and transformer pipelines. So for our categorical features, doors is a special case because it's already numerical. Categorical features equals make and color. Now what we're going to do here is create a categorical transformer. So this just means modifying the data. And to do so, we're going to use a pipeline. This is the first time we're seeing pipeline. But the steps in the pipeline are going to be first, we're going to fill with missing values with an imputer. So this is where the pipeline inputs take steps to take, right, one after the other as a list of tuples. So let's see this happening. The name is imputer, and we're going to, remember this is the action to take. So simple imputer strategy equals constant, and then the fill value is going to be missing. So you might be able to deduce what's happening there with this particular case. We're imputing the categorical features with the constant value of missing string. Now we're going to create one hot and go one hot encoder. And to handle the unknown, so columns that it hasn't seen before, we're going to tell it to ignore them. Wonderful. And then we'll make sure that we've all lined up these things. So we're going to need two. We're missing something here. We need to check where our brackets are at. We're missing one here. There we go. See, half of this is figuring out where your missing brackets are. And then door feature. We're going to define our door feature equals doors. And so the same thing again. So we're going to create a door transformer. Door transformer equals pipeline. Again, we're using a pipeline because this will all make sense in a second, right? Why we're setting up pipelines. So to do this, we have to press imputer. Then we want to do the same thing again, simple imputer. And the strategy is going to be constant. And the fill value for our doors is we're just going to fill it up with 4s because 4 is the majority number in the doors column. Then next, we want numeric features. So our numeric features is our odometer column. KM, wonderful. And then we're going to create a numeric transformer equals. The first thing we're going to do is pipeline, steps, equal, and then again we need to impute values here. So imputer, simple imputer, strategy equals mean. So this means it's going to fill the numerical columns, in our case the odometer, with the strategy mean. So it's going to take the mean value of the odometer column and fill all of the missing rows in odometer with the mean of the rest of the values. Whew, that was a lot. Now, still not done, that's all right. We're going to set up the pre-processing steps. So remember what we need to do. We need to fill missing data. So this is part of our pre-processing. These two are pre-processing our data, and this is modeling the data. So our pre-processing steps are going to be fill missing data and convert data to numbers. So we can do that. We're going to fill missing values, then convert to numbers. So to create a preprocessor, we'll instantiate a preprocessor using column transformer, tab autocomplete, and we're going to pass it. Column transformer takes transformers equals, and now this is going to be a list of the transformations we want to do on our data. And in our case, we have one called cat, short for categorical. So we're going to pass it the categorical transformer, and we want those transformations that we've defined up here, the categorical transformer, to fill the value, simple imputer, with missing, and to one hot encode, make and color. We want those to be performed on the categorical features. We'll press tab autocomplete, categorical features. Wonderful. Now we pass it another tuple. So now we want it to do same steps, but this time using the door transformer, which is going to fill the door column with the constant value of 4. So we can go door feature. Wonderful. And finally, we wanted to finish up using the num transformer, which is going to take our numeric transformer and perform the imputation on the numeric features. Beautiful. When there's only one feature, so features as a plural is probably not correct. And now that we've done our pre-processing, right? So our data is getting filled, the missing values are getting filled, and then it's getting converted to numbers using what we've done here. The next step is to create a pre-processing and modeling pipeline. We can do this, as you may be able to guess, because I've used the word pipeline. We need to create a pre-processing and modeling pipeline. So now essentially what we're doing is we're putting our pre-processing steps together with a modeling step. And because there's multiple steps, we'll use a pipeline to combine them. So model equals pipeline, and pass it steps, which is a list containing tuples, and this is the name. So this is a pre-processor step, and we're going to pass it pre-processor. So the first step in our pipeline here, our model pipeline, is to run through this. And then the next step, we'll put a little comma here, we need to create another tuple, which is going to be our model, is our random forest regressor. Wonderful. So now we've got our model pipeline set up, which will go through pre-processing. Once the pre-processing is done, it'll build a random forest classifier on it. We can get our data ready. So split data, x equals data dot drop, We're going to remove the price column because that's the one we want to predict. The axis is going to equal 1. Y is going to be data, price. Then we're going to create xtrain, xtest. As we always do, ytrain, ytest equals train test split, x, y, test size, we'll use 0.2. And then we're going to fit and score the model. So model.fit xtrain, ytrain. Now model.score xtest, ytest. Where have we got it wrong? Handle unknown. We got a typo, of course we do. Handle unknown. There we go. Change that. Woo! We did it. We did the entire pipeline in one cell, taking advantage of the pipeline class. So let's step through what we did. We imported the classes to get our data ready. Pandas, column transformer, pipeline, simple imputer, one-hot encoder. We imported the classes to do our modeling, so random forest regressor, train test split, grid search CV. We set up a random seed so our results are reproducible. And then we define different features and transformer pipelines. So we define the categorical features here, the door feature, the numeric feature, and then for each of them we created a few steps for our pipeline to take to not only impute missing values, but to one-hot encode, so turn all of our data that wasn't numbers into numbers. And then we set up a pre-processing step. That took all of our pipelines here to take the steps that we wanted to take on the categorical features, on the door feature, and on the numerical feature. Then we created another pipeline to put all of these steps together to not only pre-process our data and then model it. So then we split our data into X and Y and then into train and test. And so when we call model.fit, it's going to call this variable here, which is going to run this pipeline, which inherently is going to call the pre-processor step, which is going to run this pipeline, which is inherently going to run all of these three steps. You might be thinking, Daniel, whoa, this has got a lot going on. But if you go back through what you've looked at here, you'll be able to see, you can step through it and go, okay, I'm starting to piece together what's happening. And now if you scroll right back up to where we originally did this, filling data with pandas, filling data with Scikit-learn, and then modeling it on our car sales problem, you'll see that we did it over a number of different cells. And now we're doing it. We're building a full-blown machine learning model in 55 lines of code, minus some comments, and we could probably tidy this up if we're being honest with ourselves. But now you're starting to see is that in the beginning, machine learning is very experimental. Throughout the whole thing, it's very experimental. And so what it takes at the start is just code everywhere, trying different things, seeing how they work, and then eventually you can bring it down to something like this. Put it all into one big cell in a pipeline, going through the steps that you've figured out along the way. Now, of course, we'd want to probably improve this, use hyperparameter tuning, and that's what we might look at in the next video, is how to use hyperparameter tuning with a pipeline. Slightly different to how we've seen it done with just a regular model. So take a little break, step back through what we've done here because it was a lot. Don't worry if you don't take it in entirely. Have a read through the pipeline class of Scikit-learn documentation and see if you can line up what we've done in the documentation to what we've done here. Otherwise, I'll see you in the next video. We'll see if we can improve this score. In the last video, we saw how we can put together a number of different steps using pipeline. And now it's also possible to use grid search CV, what we've seen before, or randomized search CV with a pipeline. There's a slight little difference here, and it'll make sense once we run the code. So let's go here. Actually, we'll leave a little comment. It's also possible to use grid search CV or randomized search CV with our pipeline. And now remember, the purpose of using grid search CV or randomized search CV is to try and find another set of hyperparameters. We've seen searching for hyperparameters with a classification model, but the process again is very similar with a regression model. Once you kind of learn it for one scikit-learn model, due to the fact of how well the library is designed, you can use those principles for other types of models. And now let's see how we could use it, grid search CV, to find better hyperparameters, better settings on our random forest regressor, and hopefully improve this score. So let's type it in here. Use grid search CV with our regression pipeline. So the first things first is we create a grid. So pipe grid. So this is going to be the grid of hyperparameters our grid search CV is going to search over. Now the main difference here comes in how you set up the keys of your hyperparameter dictionary. Let's see one for example, then we can talk about it. So preprocessor underscore double underscore, sorry, num double underscore, imputer double underscore, strategy. Whoa, you might be like, Daniel, that's a lot of underscores, double underscores, and what is even happening here? Well, let's finish this out and then we can have a look. So if we're having a look at this, what is this key referring to? So if we go back up here, if we look at our pipeline, the name of this step in the pipeline is preprocessor. Okay, so you're saying you can line up those, and then we've got a double underscore here. So it goes to num. So come up and have a look into our preprocessor. Then it's going to step into our num. Okay, that's starting to make sense. So num, and then imputer underscore strategy. So if we have to refer to num, so our imputer here is our numeric transformer, which is also a pipeline, which goes to imputer. Okay, yeah, that's where imputer comes from. And then double underscore strategy. Strategy. Ah, okay, so if you trace it back, it's going to say, try the imputation strategy of mean, which is what it is now, and median. So this is the main difference between what we've seen before with grid search CV and using grid search CV with a pipeline. This is where the names come in, the strings at the front of all our steps. You might be wondering before, what are these strings doing at the start? So if we want to access our preprocessor's num step, the feature, the attribute of num, imputer, and then the strategy variable of imputer, we have to do it like this. So let's step back through. So we go preprocessor, yep, this one. Then we go up here, preprocessor, yep, num, okay. Then we go up to num, which is numeric transformer. Then we see imputer, yep. And then we're going to adjust strategy. Okay, so that's the parameters for that. Now let's see how we would access our model. So we go model, double underscore, oh, shift enter again, getting trigger happy, model, double underscore, and estimators. So we only need one double underscore here because we're only going up one level. So if we access our model, which is pipeline, we want to access the model step. So this is where the model double underscore comes in. And we want to pass n estimators, which would be the same as going in here and pressing n estimators, but we're not going to do it there. We're going to do it here. We're going to pass it 100 and 1000. So again, this is just going into the model step of our pipeline, which is here, and passing random forest regressor and estimators, these two values. And then we can do the same for other features that we've seen before. So model underscore underscore max depth. Then we're going to pass it, let's go none, 5. And then we'll go model double underscore max features. And then we're going to pass it auto. Actually, yeah, we'll just keep it as 1 there, just to save some time on our grid search. And we'll go model double underscore min samples split. I'm going to pass that 2 and 4. Okay, wonderful. So now we've got our parameter grid set up. How would we run grid search CV? So this is where we've already imported it up here. We've imported grid search CV from model selection. But from completeness, or for completeness, what we might do is do it again. So from Scikit-learn.model selection import. You don't need to do this if you've already imported it, but we're just doing it so you can see where it's from. So from Scikit-learn.model selection import grid search CV, we're going to create GS model, grid search model, grid search CV. We're going to pass it our model, which is, again, here, in the form of a pipeline. We're going to pass it pipe grid, which is this dictionary here of different parameters it's going to search over. And then we're going to pass it CV equals 5 for 5-fold cross-validation. And we'll pass it a verbose level of 2, so it prints out a little bit of progress for us so we can see what's happening. We go gsModel.fit, and it's going to go xtrain, ytrain. Beautiful. And so this is going through 5 folds for each of the 16 candidates. If you wanted to work that out, you go 2, so 2 variables here, times 2, times 2, so that's 2 times 2, 4, times 2, 8, times 1, 8, times 2. So that's 16 different combinations of parameters. We're doing 5-fold cross-validation, so it's going to do 16 times 5, which is 80. So once that's finished, here we've got an output here of all the different versions of parameters that it's doing. And once it's finished, we'll be able to evaluate our grid search model using gsModel.score and pass it the test data. So this is the score we got before without grid search, so just the baseline hyperparameters of random forest regressor. Now you might need to wait, depending on how fast your computer is, you might need to wait a little while. So this is why it's always important to be careful how many parameters you pass to grid search CV, because it is going to exhaustively search every single combination. So what we might do is pause the video and wait until our model has finished training and then see what its score is. Excellent. So after about a minute or so, our grid search is finished, and we can see that if we evaluate our grid searched model, it gets a score of 0.333. Now, versus our original model score of 0.182, that's pretty damn good. That's almost an improvement of double by searching for different hyperparameters using a grid search. Now, we could keep this going for more different parameters, but in the sake of time, we're going to leave it there. And so, we've covered a lot, and if you've made it this far, congratulations. Let's have a look here. What we've covered. Shift Enter. Oh, what we're covering. It should be what we've covered now. So we've gone from an end-to-end Scikit-learn workflow. We've seen how to get data ready. We've seen how to choose the right estimator/algorithm for our problems. We've seen how to fit models/algorithms and use them to make predictions on our data. We've seen how to evaluate models. We've seen how to improve models. We've seen how to save and load trained models. And now we've just put it all together using a pipeline. We fit everything that we did before that took multiple cells before into one cell. One cell of a Jupyter notebook, we've got our entire pipeline using Scikit-learn's pipeline function. Now, if you've made it this far, it's worth patting yourself on the back. So congratulations, we've covered a lot of ground in the Scikit-learn library. But as you might have guessed, there's a lot more that's still there. But with what you've learned so far, you'll be able to take it on. Right? You'll be able to look at things, you'll be able to look at Scikit-learn workflows, you'll be able to look at different machine learning problems and go, okay, I can kind of figure out that I have to get the data ready first. I can see if I can choose the right estimator/algorithm for our problem. I can go through trying to fit my model to the data and make predictions. Then I can try and evaluate it and improve it, save and load it. After I've done a lot of messy code, I can try put it all together and clean it all up. And don't worry. Putting all this together, it's not like you're going to learn it overnight. I don't expect you to, even after going through all the videos that we've covered. It's going to take a lot of practice, right? And hopefully you can use the resources that are available to you. So all the code that we've got here, it will be available in the resources section. It will be available in a notebook you can refer back to. But if you're looking for somewhere next of like where you want to go, the best place is the Scikit-learn documentation. Scikit-learn documentation. If there's something that sticks out to you on something you want to learn a little bit more of one of these topics that we've gone through and covered, something you want to dig a little bit deeper into, maybe you want to look at different classification models, regression models, or clustering, something that we haven't seen much of yet, go to the Scikit-learn documentation, go to the user guide, and step through all of these different categories here, and see if there's a little topic here that you want to read a bit deeper into. And again, It's going to be a little bit overwhelming to begin with, but with practice, you'll be able to start to make your own mental models of how you can use the Scikit-learn library to solve your own machine learning problems. Now, with that being said, I'll see you in the next section. And we're going to put everything that we've learned in the previous section, section 2, all these tools that we've learned, we're going to put them together and start to work on some of our own projects. So take a break, revise what we've learned, check out the resources, check out the documentation, and get yourself excited for the next section. I'll see you there.